till second symbol of the P sequence, right? Till the 5th frame, right? So this can be, this is frame 1, this is frame 2, this is frame 3, this is frame 4, this is frame 5, right? This is one packet scenario that where the packet breaks in between. The other packet breakage can be at the card itself, right? The another scenario could be where you are completely getting the first packet and you're not receiving any packet at all. That means that your USRP might start sampling right from between. That is your, this is your PI packet, this is your PI minus 1, right? The USRP might so happen that it starts sampling it something like this. This is your PI minus 1, sorry. This is your PI and this is your PI minus 1. It also so might happen that the USRP samples from here. So it depends upon from where the sampling has occurred, and based on that, the packet fragmentation might occur. Okay, so we have to kind of figure out where the fragment is, and based on that, reconstruct it and parse it back in the best way possible. Right. This operation is also done on the MAC layer, actually on the kind of in the lower MAC layer, when you are moving to an end-to-end network communication. When it is not just a physical layer, but you have the L2 and the L3 layer also. There actually it is being done. It is being done on the MAC. So the packet rearrangement, you can leave it for the time being on the transmitter side, or sorry, on the L1 side, and you can move it to the L2 side also, just for the clarity. Okay. Now coming to how you need to actually make the architecture for the code, right? Stop. So this is you will not do an exercise on this code. Okay, this is like a architectural code. So there are a lot of things that has been taken care of here, and will not be a good idea to do a coding here. So we'll give us very simple way of coding in the exercise in the next session. So here what you have to do is, so what we are doing is, here you see that there are the configuration information, okay, of the USRP, right? These are the configuration information, okay? Then there is a channel coding, right? Then there is the packet structure that we're using, the filter parameters. So we are using root raised cosine filter, right? The pulse shaping filter, as I told you. So this is the root raised cosine filter that I'm using. Currently, we are only working on text because the application that we made for one of our customers was on text. We are also including the audio and the images in next version release for them. So this is what the text is. Then we have the TX constellation that you will be able to see. This will be more like a clean constellation because this is just on the software only. I'm actually telling you because there is no other way that you can actually take the TX constellation unless and until you take another USRP and check it on the receiver, right? So this is a TX constellation, the I diagram, the IQ waveform, right? So what happens is the user gets to set up the entire packet, right? You can see this data bits per packet. There's a packet structure. If you want to change this, you can change this, and the filter parameters, right? So based on that, what we do is we configure it on the front panel, right? Actually, there is one problem in this code is that the scrolling bar becomes a problem. Otherwise, you could see what we have done here. Upsampling, after upsampling, actually there is the pulse shaping filter actually. Okay, so but yeah, like there is a problem with the horizontal bar. That's why I'm not able to move the code. But whatsoever, like we can see that the entire block diagrams that I made is kind of made here with another another thing which is not visible right now with you is the pulse shaping filter. Okay. So in this, what we have done is we have kept one loop, okay, for the data generation. Okay, so here the bit and the symbol operation takes place. Okay, so here you can see that there is this message that is coming in, converting to bits. Convert to bits, then you have the TX packet. Sorry, then you have the convolution encoder and the Hamming encoder, right? So this is the Hamming encoder. This is the convolution encoder, right? And this is the data to bits. Once you are done with that, you move towards the generate packet size, as I already told you, because now your channel coding is done. So you move towards the packet size. You took the information from the user as in how the packet structure needs to be. And based on that, you appended it. So for the time being, what we have done is we have used PN sequences, pseudo noise of a particular orders. So I think we have used for sync as 9, and for training sequence, I have used 15. Not very sure about it, but like, yeah, we have used either 9 for the sync and 15 order for the training. We checked out during the development time, we checked out whether they have a correlation, and they were kind of off. So we use a 9 and a 15, I suppose, on that. Okay. So what we do is we generate the packets, right? And after that, we do a symbol, a bit to symbol mapping, right? So once we are done with the symbol to bit mapping, you can see that I got back my symbols now. In this, I will have my symbols, right? From the symbol, what I do is I do an upsampling, right? You know the process of upsampling. I will just explain this transmitter block anyway. I'm going to explain each and every block. So I'm going to come back again to this, but let me just at least tell you overall the picture, and then I'll come back to the block. So you do the upsampling, and after that, there is a PX filter. Here, I've implemented using a math script, node. See this. So this is the filter that I have implemented using a math script node, right? This is an RRC filter, and the filter response looks something like this. Okay. I'll come to that again. Right. And then after this is done, we get the waveform. Sorry, not get back, but we get the waveform. We get the waveform, and then we use something called, so this architecture is basically built on a combination of state machine plus a producer consumer architecture. We are using a producer consumer because the producer consumer architecture is an architecture which is normally used when you are acquiring or transmitting the data and at the same time processing it. This is kind of parallelizing, or so to say, running parallel loops such that there is no data overflow or underflow. Normally, another thing from my experience, I'm telling you that when you're working with USRPs, there is an intrinsic problem. That is something that I have seen over my experience over USRPs, is that the buffer overflows and underflows are a very big issue. And maintaining the buffer rates is something that requires a lot of precision in terms of coding, as well as in terms of like the calculation that you do, in terms of like how much you are acquiring, what is your PC's capability of taking a stream data and then processing it. So there is always a necessity to actually, parallelize the generation part from the acquisition part, or so to say that here, this part is completely a software part, this loop, if you see. But the next loop where I'm pushing my data to is using the USRP device drivers, right? This is using the USRP device drivers, correct? So what we do is we prepare the data in one loop, and then on the next loop, we do nothing but to just write the data on the USRP. So what happens is it becomes parallel, the loops become parallel, and the processing complexity of the code does not interfere with the generation part. That means this loop would be, once the data is prepared, this loop can run independently. It is not an inline processing or inline generation that we are doing, right? So with that, we followed a producer consumer architecture wherein this data is being produced by the first loop, and then it is actually given to the next loop or the second loop, which is called as a consumer loop. And then we are having state machines in between them. You can see this. We're having state machines, something like this. So whenever you run the code, we do certain validation of this. We used to generate the data, then we used to, validate the set. No, we used to validate the setting first, then generate the data, then do the channel coding, and then transmit the data, right? And then if you press basically stop, it shuts down and goes to an exit state, right? And both the loops are being stopped at the same time using a synchronization method, software synchronization. Okay. So you can see that we have used the you can see that we have used different methods in between this, right? for us to get the data from different sources. So it can be from a file, it can be handwritten, it can be copy pasted, right? And now when we're integrating the audio and all, we're also integrating it with the microphone, so that people can speak to the microphone and it gets sent automatically. This is primarily for making it completely into a radio set with some particular functionalities, right? And then you can see that here I have used the basic, very simple VIs that we have done yesterday, right? We are using the device drivers. The device drivers has nothing much in terms of, in terms of like coding or programming. It's very manual. It's very pedantic. It's very methodical, that you use this device drivers and just get done with it. There is no innovation in it. The main part is actually on the DSP side of things, right? This is so the good part is that you don't have to worry too much on like, generating the data. The USRP will, if it is working fine, it will generate the data. So then you can only concentrate on your particular algorithm or in your own particular area of research, such that you can get the things sorted in terms of the algorithm, in terms of the IP, and then just try it out on the USRP, whether it's working or not, right? So normally on a packet-based architecture, it is advisable that you use a consumer producer consumer architecture with a state machine involved, such that you can validate the setting, generate the data responsibly, and then control the flow of the program in a way which will allow you to stream the data without having much difficulty in terms of the data transmission. Okay, so this is the transmitter part of things, right? Now, the reason that I use a root risk assign, because I'm moving towards the receiver, overall receiver part also. That's why it's important to give an overview on the receiver part. So on the receiver part and on the transmitter part, what happens is we're using two RRC filters, right? The reason of using two RRC filter is because if I just draw the baseband diagram of the entire flow, in that case, you know that if I'm basically having, if this is my received signal, y equal to y received is the received signal, then you will have H that will be convolved with S, and that will be again, S will be the symbol transmitted, right? And then there will be an AWG channel, right? So this is basically typically the model that we all know about, and that is something that we use, right? Now, the idea is that we have to, first of all, there is one way is to nullify the effect of this, right? And at the same time, I have to also take into care the ISI, which is also available on the receiver side because of the intersymbol interference, right? Because all of the wireless signals will follow different multipaths, right? In our scenarios, when we are using just in the lab, the multipaths may not be that very prominent, but when you actually increase the separation of the transmitter and receiver, this multipath effects, as you might already know it, will come very much into prominence, right? But normally when we are testing it on the lab, since the lab setup is not very crowded or it does not have an actual channel effect in case, it may not necessarily use a channel equalization or a channel estimation also. But when the separation increases, when there is no line of sight, your channel becomes from Bayesian, you move towards a relay-based channel, you will require, because the SNR will drastically decrease after that, right? So all precautions need to be taken care of. So what we do here is that in order to increase in order to mitigate the intersymbol interference, the ISI, we also convolve this. That's the reason why we convolve it with a GRRC, right? Two reasons for it. One is that, one second. So the one reason is that when we are generating the data on the TX side, right? So what we do normally, so you have a stream, for example, right? Let me just take this part of the board. So suppose, for example, you have a stream. Let us take the symbols itself, 00, 01, 10, 11. Okay, I'm using a QPSK scheme on this. So when I'm using a QPSK scheme, this is 00, 01, so 11 and 10. Okay, so this will be represented by 0.707 plus J 0.707. This will be minus plus minus minus plus minus, right? The values remain same, 0.707, 0.07. So now when we are actually coding it, what happens is for 00, you will have an I and you will have a Q, right? So for I, let me draw it this way. This is your 0.707. This is your minus 0.707. So again, 707. This is your minus 0.7. So this is your 0.707. This is your minus 0.707. This is 0.707. This is minus 0.707. So now what we do is, suppose the bit stream that is there is 00, 01, 10, 11. And because we are using a QPSK scheme, that's why I have divided into 00, 01, 10, 11. And this will be your symbol period, right? This will be your symbol period. Now, when it is 00, then this will be 0.707, right? When it is 01, it will be minus 0.707. Then again, when it is 10, this will be again 0.707. And then when it is 11, it will be like this. Right? So you have typically a pulse like this. Right? This is the pulse. Okay. So when you are having a pulse like this, right, what you do is, now you see that this pulse is obviously something that you would not like to transmit, right? Because as you know that the high edges or the sharp edges of the pulse will inject more high frequency. So whenever you are trying to send the same thing through RF, there will be a lot of power dissipations because it is a square wave finally, and the square wave is composed of several harmonics, and there will be power dissipation on the harmonics. So never a good idea to do a pulse, never a good idea to actually, send a pulse to across the air, right? There's the reason why whenever you are going for radar applications where it requires pulse, you are having a very high power for that, right? Because that there is enough power for you to transmit the pulse. In general scenarios where we are doing telecommunications, like or sending data, we obviously try to not have very huge power amplifiers at all. That is the reason why what we do is we try to pulse shape it, right? So we'll try to pulse shape it. When we pulse shape it, we need to actually smoothen the curve like this, right? So when I'm smoothening the curve like this, what I'm essentially doing is I'm basically removing this portion. I'm removing this portion. I'm removing this portion. I'm removing this and making it into a pulse shape. Now, how we do the pulse shaping? So what we do prior to the pulse shaping is that we do an upsampling, right? When we do an upsampling, each of the samples that I will be having, I will be defining an L, or so to say, samples per symbol. Suppose I say 4, then what I do is I induct or I induce L-1 zeros with this, and then this zeros gets inside here at this points. Okay. And then I define a root raised cosine filter, which is the guy who does this. I define this root raised cosine filter, and this waveform, digital waveform, right, with zero induced across between each samples gets convolved with this root raised cosine filter, which is essentially a low pass filter with a particular bandwidth, and the bandwidth is something that is controllable using the filter length and the filter parameter, that is the alpha, the roll-off factor. As you know that the roll-off factor is inversely proportional to the bandwidth, right? So if you want to increase the bandwidth, you have to decrease the alpha, and vice versa, right? So it's inversely proportional. And also the filter length, that means the number of taps that you require. Based on that, you can have an LPF with a particular frequency, and then when it gets convolved with this root raised cosine, what will happen is this same signal would now behave like this. So now there will be a smoothing of the curve. Similarly, same thing will happen here as well. So there will be smoothing of the curve, and you would be able to band limit the signal for the channel, right? Otherwise, what would have happened is if you would have sent this signal, then the bandpass filter, the analog filter, which is there, you can see this in the architecture. There is a filter, the low pass filter, which is available on the RF front end also. So that filter would have distorted the signal completely. And firstly, it would have got distorted. Secondly, in the power amplifier stage, it would have got this, the power would have got dissipated, right? Because of all these reasons, you're using a pulse shaping filter, right? Now, once you do that, so you have now your equation, actually this equation becomes y equal to g RRC, that is from the pulse shaping, S H plus N. Now this is your what is being received. Now once this is the received part. Now once it goes to our DSP block on the receiver, on the DSP block, we do a convolution of YREC received with a match filter, which is again a root raised cosine, but with a match filter, right? So when we do that, what happens is your Y at the match filter would be equal to GRRC pulse shaping convolved with GRRC match filtering convolved with S convolved with H plus M, right? And also it will get convolved with. So in any case, we can neglect this part. So now you know that when a root raised cosine, this is a mathematical identity. Then when a root raised cosine is convolved with a root raised cosine, you get a raised cosine, right? When you get a raised cosine, it is similar to a sync pulse, right? So what will happen is, if this is your symbol, then this will flow through the nulls, right? This will flow through the nulls. If this is your second symbol, which is placed here, it will, I'm not very good at drawing, so like it will move like this. And if this is your third symbol, for example, so please, please don't mind the bad drawing. This is how. So you see, when I'm sampling it now, across this, when I'm sampling it, I don't get any. So when I'm sampling this, I don't get the energy from this. When I'm sampling this, I don't get any energy from this or this, so on and so forth, maybe, right? So having it sync, where having it converted into a sync now, what happens is that you can just think it this way, that if you do a Fourier transform of this, what will happen is your G, it will convert into multiplication. That is your GRC convolved with GRC will be a raised cosine, which will get converted into a frequency domain pulse, right? Into a square pulse, right? Of a particular bandwidth, right? And then it will limit because it will multiply the symbol will get multiplied with the filter. So it will band limited within that particular bandwidth, right? So you can see this, that here, this part becomes raised cosine, which is basically a sync pulse. A sync pulse in time domain is a rectangular pulse in the frequency domain. And what you do is you then convolve it, and then there is a convolution with the S and the H. So you basically have S, H, and G. G is a rect pulse. So it will basically will kind of band limited within the bandwidth that this filter defines, right? And this is exactly what we are using. After that, the receiver follows several other procedures of also removing the H, right? So all those things will be followed on the last session today. I will not go deeper into that, but this is what we are going to do mainly, right? From we use a root risk assign filter on the pulse shaping side, we use a match filter on the root risk assign on the match filter side, and hence we are able to band limit or mitigate the ISI. Once the ISI is mitigated, we know about it, then we move forward and go towards the symbol timing recovery, then other DSP processes which are required, right? So on the receiver side, this is the transfer.
Maybe participants, just I will be sharing you the link for today's attendance. So just please go through that and mark it. Now, Nilupal, you may please continue.
Yeah. So on the receiver part, what happens is on the receiver part, what happens is the receiver is a bit more intensive. Okay. So what we do is we keep a mean receiver loop. Okay. This receiver loop takes care of the only of the streaming part. That means whatever waveform I'm getting, that waveform it is being taken care of. So you can see this. There are a lot of three steps which happens. Receive the data. That is, it is receiving the data. Before receiving the data, we actually calculate the frame size and everything. This is something that the code automatically takes care of, okay, based on the user settings. Then we receive the data, right? After receiving the data again, we use a producer consumer architecture, and using that, I push the code using some queues. I push the code from, I push the data, the IQ data, right? The received IQ data, the raw IQ data, I mean, from this first loop to this second loop, okay? And in the second loop, the first thing that I do is a match filtering. The first thing that I do is a match filtering, right? Then it follows, symbol timing recovery follows, downsample follows, frame detect, parse packet, channel coefficient, can generate. So this step actually generate the channel equalization, right? Equalization coefficients, because again, channel equalization coefficients has to be figured out from H. How it is figured out, you will get to know it. We use something called as a Toeplitz matrix, and using the Toeplitz matrix, we use a pseudo noise, a pseudo inverse of that, and with that we are able to find out the equalizer coefficients. So this equalizer coefficients are figured out from the channel coefficients, and after that it is given to this VI. It is a simple VI. Equalized channel is a simple VI where we convolve with the incoming data with the equalization coefficients. Actually, it's a simple FIR filtering that we do, but this generate equalizer coefficient is the more involving or computationally more intensive stage. Okay, then there is this demodulate, that is your symbols to bits. That is simple, and after it goes here, this is something which does a similar work like what you call as the dash protocol, you know, which is used for dynamic adaptive streaming, mainly something that YouTube uses, right? So what it does is it basically waits for a certain amount of packets to come in before it starts streaming the packet to the user, actually. Okay, so that is being taken care of in this particular part. So very clearly here, this receiver is very well distincted, wherein you are having the IQ waveform here, you are having the symbol here, and you are having the bits here, bit processing here. So here what happens is, after several three steps, you can see this, we wait for the buffer to fill, that is, we are doing the buffering stage now, right? Then we are going for the sort packets, right? We sort the packets here. Then we go for the decode packets. That is, when you go for the decode packet, you are now you have it in the bits. So you are already modulated. So now you have the encoded bits. Still, you have the encoded bits. So we, depending upon the user selecting the hamming or the encode convolution encoder, it basically removes the encoding part, gets it decoded, and gives the actual data to the text to bit to the bits to text converter. Once that bits to text is done, you convert that into text, and finally this goes to the user for reconstructing back your packet. Okay, so this is the overall flow of the transmitter and the receiver, right? lot of processing involved, I know. That's why we have kept the session in a way that it does not, it is not too much for you to also absorb. So this is particularly the transmitter and the receiver. Okay. On the transmitter part, just to go back to the transmitter part, very simply, we generate the data bits from the file or from the user. If it is from the file, we generate from the file. If it is from the from user given randomly at that point of time, it can be randomly taken. Or if it is an audio, video, we are also encompassing that in our next version. So whether it will be from microphone or whether it will from the from a WAV file, so that will be taken care of. When it's an image, it's a PNG, then we have to take care of that. Then again, if it's a video, then we have to use compression algorithms onto it, such that we can band limit it within 20 megahertz of the USRPs, normal USRPs that we have. Again, there are USRPs which are having 200 megahertz of bandwidth also. But even then also you will require data compression when it comes to video. Okay, so whenever you're trying to do video streaming, there is a necessity of data compression. Then we validate the settings, and once it is done, then we go for channel encoding it, and then transmit the data. So once the transmission is done, then you basically go through this block. The first block is text to bit convert. Then, sorry, text to bit convert, correct? Text to bit convert. Let me just take the context out. Yeah, text to bit convert. Then you have the convolution encoder and the Hamming encoder, right? And we have kept one possibility of, like, putting some custom encoding codes also here if required later on. Then we have the generate packet, map bits to symbols, upsample, pulse shape, right? And then this same thing goes here. Okay. This is how it works, how the code works mainly, right? And this is typically a transmitter and a receiver application that you will see. Normally, when it comes to 2G, 3G, or 4G packet-based communication, the packet structures would be defined already, right? The packet structures will be defined. You have to follow that ETSI standards, and there will be, for an end-to-end network communication, there will be the L2 layer and the L3 layer. So there will be the RRC layer, which will be controlling the several things on the packet, specifically the AMC part of things, like the automatic modulation coding scheme of it. Then there will be the L2 layer, right, which will be controlling the packets, as in, like, it will be helping you, it will be incorporating the packet restructuring, the packet repacketization, it will packet shuffling. All those things will be taken care of in the L2 layer mainly, right? So this is purely a demonstration on the L1 layer, right? Because the USRPs are typically very good for actually prototyping the L1 layers, mainly because it has the RF front end. It can work through, you can work on three levels, that is bits, symbols, and waveforms. So it's very good for very good as a platform for actually prototyping the L1 layer. Okay, I think I'm majorly done for today, for in this part of the session. Okay, if you have any question, I would like to open this discussion for questions mainly. I think you should have a few questions for sure, because this is a long explanation that I gave and I brought in a lot of things, right? So let's take some time to discuss among ourselves, right? We have around like 13 minutes more. So let's discuss about this about like 10 minutes before we wrap up. Okay. Any questions, please put it forward over the chat, or if you want to discuss verbally also, that is also possible. Yes, participants, please. It cannot be so that you don't have a query, right? Because there's so many things, and I'm pretty sure, like, even though I'm trying my best, but I'm not able to relate 100% of what I can. So there will be certain gaps. So you can ask me the question. It is okay. Meaning, like, if it is not a very sophisticated question also, then also it's fine. I will be able to handle it, and I will be able to answer that mainly. That's not a problem.
Hello.
Hello, yes.
Sir,
Yes.
So here there is a data loop count in the middle.
Yes. Yes.
Yeah, yeah.
This one.
So yes, sir.
Yeah.
So how it works means it gives what? It will indicate what?
It will indicate the amount of time this while loop has iterated. Okay, so whenever you require this for maintaining the data rate, right? Because here your packets will get generated, correct? So how many packets are getting generated and at what rate it is getting generated, we'll be able to get it from this data loop count mainly. As you might be already knowing, this I which is there gives you the number of iterations that the while loop has iterated, right?
Yes,
So
sir.
this is typically the number of times the while loop is iterated, or so to say, like how many packets you have generated. Mainly. You can take it that way also, because we generate the packet and push the packet to this one.
Okay. And so that text preview shows how the data is being processed here in pink box. There is a text preview above data loop count.
Which one you're saying?
So in the middle only, text
Yeah, the text
preview.
preview,
Yeah.
how the data looks
Yes.
like. This is pretty straightforward actually. This is actually this one. This one. This part only. As in, what is the data that you are sending? This is simple. This is like, what is the data that you're sending? Just a text preview being. Okay. We're using a local variable for that.
Okay. Thank you, sir.
See this? This is the indicator. Sorry, the text preview is this indicator actually. This
Thank you, sir.
So the next session would be a hands-on on this. Okay, we'll be sharing you this codes. You can keep it also because that will help you to have a basic foundation on like the basic structures. So we'll give you a code. You have to kind of make the code on that. I hope you all have received the exercises. Okay, if not, then you can contact IIT Jammu. They will provide you the exercise. Okay, and the exercise will be taken up by my colleague Aman. Okay. Can you just reply to me over the chat whether you have understood or not? Mainly like the at least 50% of the thing that I explained. Okay, let me ask you then a few things. Okay, what will happen if I basically put the alpha as 1? Anyone? What will happen if I put the alpha as 1? What will happen? Yeah, I'm expecting some answer. It has to be, yeah, the rule of factor. It will be a steepest curve, correct? So it will become more shape square. It will become like a very selective filter, right? It will become very sharp, maybe, right? So the bandwidth will decrease, right? And it will become a very narrow band filter. And in fact, like an alpha in a today's sense is kind of not possible, right? So it will become a very sharp selective filter, maybe a narrow band filter, correct? Okay. Suppose I need to now the same code you will see tomorrow that we would be using an OFDM somewhere here, okay, after this, and we'll be converting it into an OFDM code, okay, and you can cater to multi-users after that, actually. So the whole purpose of the OFDM is to actually cater to multi-users, right, using the subcarriers. So we are going to demonstrate that tomorrow, okay, using an OFDM structure. Fine. If there are no other questions, in that case, I will log out from the session now. Okay. If there is any question, you know, you have my email ID. You can send it to me. Okay. And Amal will be joining you in at 11:45 p.m. Okay. And the session will go till 12:45. If you have not received, any one of you who have not received the exercise, please inform the organizers and get the exercises from them. Okay. This is very important because the session is only of 1 hour and it is going to take 1 hour time in order to do the exercise. Anything else from the participants? Okay, fine, cool then. So Amit, sir, you there?
Hello.
Hello.
Okay. Actually, it was a request to send the recordings of the session because if we miss something or we are not able to understand at one instance, so we can watch it again and observe the.
Right, ma'am. So I think the recording sessions are available in YouTube only. I think the organizers will be able to direct you there, ma'am. But we are recording it for sure because the recording happened.
Yes, because I have requested also through mail, but I didn't get the response. So that's
okay.
It's already emailed to every participant, and every time we will not mail at every day. Just have a look and go to the channel as per your convenience. They are being uploaded every day at 9 p.m.
Okay. Thank you so much.
Thank you.
Yeah, Amit sir, I'm done mainly. Okay, so Amal will join in 11:45.
Okay, so let's have a short break, maybe as per our schedule.
Yeah.
Okay, so
Thanks,
participants, now we are going for a short break. Till what time, Nilutpal?
11:45, right, sir? 11:45 is the next session. So I'm just wrapping up 5 minutes earlier.
Okay, no problem. So we'll be back by 11:45.
Yes, sir.
Okay.
Transmitter, and let's say enter something additional. As you can notice, if you go back at the receiver, you can notice that is getting updated. So this is a simple packet transceiver, okay, which we are seeing over here. So I'll go to the block diagram of the transmitter first. Let's just quickly see what all are there. So the USRP code, as I see, this is the first set of APIs, the open USRP session. Then what you have is a configure signal. This is the write VI, and this is the close session. So you have only 4 VAs over here. So this is exclusively to just control the USRP, nothing else. All you're doing is configuring a certain set of parameters. and then pushing the data over to the USRP using the write function. Now, quickly make a couple of changes over here. Okay, so this is the USRP part of it. These 4 functions, which is available where? Which is available in the instrument IO, instrument drivers, NI USRP palette. These are the 4 functions that we have used. Okay, and then on the top, what we have, these are the actual functions. This is a heavily scaled down version of what was shown to you before by Nilutpal. This has 5 independent functions which you will be building in this. Some of them you will be building, some of them will be given to you, which you will be building to kind of, this is the message text. So to kind of take the message text, convert that into a corresponding ASCII character. So I'm just explaining the process flow one by one. So this is the message text. The next function is a string to byte array. So essentially the string that you are obtaining, you're converting that string towards a byte array. So each byte, right, each data point, it contains the ASCII code, the numeric of the ASCII code numeric corresponding to the one character. So this is an entire array that will contain all the message text in ASCII numeric data. From that bytes, there is a function that converts it to bits. Then following that, you do a Golang encoding on the data, okay, which is a process that you will have to do at the other side also. You have to kind of decode the data. Once this is done, so this is essentially a single packet. This data, you have just taken the bits, you've taken the encoding on that, you've done the encoding on that. Following that, you have 3 processes which are the most critical. The first one being, you are essentially receiving the data set, but as I discussed in the first day, the second session, the synchronization, the moment you're sending packets, a very critical part of that is synchronization. So how do you synchronize the frames as it is received would be a critical question. So to that, we had an answer. We said that we would use synchronization bits. We would have synchronization bits in place to detect where a frame starts. And then from over there, how many characters are there, you take that or retrieve that exclusively. Then following that, you decode that. So over here, we have to frame the packet, we have to kind of design the packet in such a way that these, essentially these bits are converted to a frame structure. Now, what are the components of this frame structure? This is there on the front panel. If you see, I have guard bits and sync bits. Sync bits is the important part. Guard bits is something that will be available in that'll be part of the packet. We had shown the packet structure also that time. Let me just do one thing. Let me just quickly bring that up as well, so that okay. So essentially, this what you see over here, this is what the structure of the packet is. So there will be a guard band. Then there'll be a synchronization sequence. Instead of packet numbers, what we will be putting is the packet, number of data elements in the packet. It's a slight tweaking, and then zero padding. So the initial part, which is this, you notice my mouse pointer where it is as it is moving from here till here, is done in this function, which is bits to frame. So the bits to frame function, I'll go into the block diagram here. So the bits to frame function, you don't need to do this right now. All we are doing is we are taking a specific number of guard bits. You are saying that it is all one, okay, and we are kind of padding it to the beginning and end of this array that we are going to transmit. So this function, what you have here, it's called a build array function, which is used to build an array with the input data coming in. So your actual data, your original data is coming in from here, which is given as an input towards this. So the actual data is coming in through, sorry, your actual data is coming in through here, and then the synchronization, part, the sync bits, as you say, are used or are implemented by using a generate bit function. There is a generate bit function in a modulation toolkit, which essentially gives a Gallo sequence, a p-order sequence that is of a definite number. So if you do not specify anything, it will create a PN sequence order of 9. Okay, and this with number of bits as you specify. So this parameter, meaning the synchronization parameter, has to remain same in both transmitter and receiver, right? So you are pushing that towards this function. So essentially what you have here is guard. First one is guard, then sync, then the encoded data, and finally again one guard. And this frame to transmit is what gets passed out. The frame to transmit, it comes over to the next function, which is frame to IQ data. Now this, the frame to IQ data, this is the most critical function in this entire exercise, wherein we are taking the data as it is coming in, okay, and then bringing it directly to the modulate function. So the modulate PSK, the modulate PSK function directly takes this and then gives out the IQ data, okay, IQ baseband data. So till here, the data is purely digital. It's bit sequences with all the padding that you've done, with the packetization that you've done. It's still a digital data set, digital data, which you're pushing towards this modulate PSK function, of which the output is IQ data. Now, the two inputs to this, again, we have discussed this before, and I'm sure others also would have introduced you to these functions. After this also, there are these two functions. First one being generation of system parameters. The next one is generation of filter coefficients for this function. So these two are a mandatory thing, kind of, which you need to obtain. And towards that, again, you have these set of inputs that is defined by the modulation and filter parameters, right? Following that, the data directly comes here. There is a scaling that you're doing on the amplitude with regards to the what amplitude is expected. So you're doing that here. You're scaling it to half, and you're pushing that data towards a bundle function that comes as an output complex waveform. And following that, you are doing an IQ padding. Now in the IQ padding, all you are doing is you're taking a data set, right, which is coming in, and then you are kind of having a padding ratio again that is given us an input from the main VA as a user. The padding data, you're essentially making a zero data array, and you're padding it to the front and back, both beginning and end of the entire packet. And this is the final complex waveform that is getting pushed through pipelining into the USRP write VI. There is also a constellation graph, as you see it over here, which is to display the data. So this is the initial part. Okay, this is the program. What you see, the transmitter, this is how the transmitter gets designed, the program gets designed. Now, one by one, we have to develop this. But before that, if you have any questions, please bring it up. We can discuss. Otherwise, we can proceed with the actual exercise, the development, and what you need to do. Anyone, any questions? Okay. Guys, please stay active. This exercise needs you to be involved properly. Okay. Okay. Now, I'll not go do the remote because remote is kind of a little unresponsive. So I'll do this on my local system. So same, this is the same thing that has been shared to you. You need to open this BI, which is the transmitter exercise. This is the one, transmitter exercise. And you can see that this is pretty much, stripped off of all the BIs or the functions that are being used. You have all the controls in place. You have everything else in place. All you need to do is program the USRP first, the USRP APIs first, and then go to this. The USRP API part should not take you more than 5 minutes. It's a quite simple thing. What do? We go to the instrument IO, instrument drivers, and a USRP transmit. Pay very close attention to this, guys. Okay. So how do we do it? We know that these are the 4 functions that needs to be used. First one being the USRP transmit function. So I'll put the USRP transmit function open session in place. Then you have the configure signal. These 2 things I've put in place. What are the various hardware parameters? The first one is the IP address that needs to be connected to this. Following that, the session is being passed through the functions like in this manner. Okay. And then we need to give these as the input: IQ rate, carrier frequency, and the gain. So the IQ rate, I'm pushing it over here. Carrier frequency. This is the gain. And this is the active antenna. So all the inputs that are required for these VAs to kind of function, the configure USRP function has been put in place. So 2 functions are already in place. And just the output of this, we have to wire the coerced values. So what is coerced values? Coerced values are essentially if these data inputs that you're giving is not in the range of the USRP or cannot be actually implemented by the USRP for hardware limitation reasons. So these are, remember, these are the tunable parameters. So I'm just passing this coerced IQ rate, then the coerced carrier frequency, and the coerced gain towards this. Now, what is the next thing? So after this is done, you have 2 next other functions. One is the USRP write data. So the USRP write data, I will again quickly wire this to the first part. Just bring it to the line. And then towards the end, what we will have is USRP close session. Again, just wire it directly. In this manner. Okay, and the error comes here, the error out. One quick thing that you can do is this. I don't know if this design has been shared with you, but this is a very simple practice to kind of ensure that if or when the stop button is pressed or there is an error in the program, I want the program execution to stop. Okay, so hope that is clear. So this is the first part of the exercise. Okay, 4 functions and the inputs corresponding to that. Okay, can you quickly do it? I'll give you 5 minutes. please wrap this up. If you have any questions on the first part, you can ask now also. Please finish till this. Guys, done? Please stay active on the chat at least. Is everyone there? So I'm assuming you have finished this part. Guys, kindly be responsive. It's very difficult to run a hands-on without any response from your side. Requesting you, please. Okay, thank you, Mr. Ben. Others? Okay. So let's go to the most critical part in this, which is essentially the core, the modulation itself. How do you do the modulation? So for that, we need our next toolkit, the modulation toolkit. Okay. So what all do we need from there? We need to do the modulation. So we know that we are going to modulate. So we will use the Psk modulation function. So go to the modulation toolkit under digital. How do you go there? Go to RF communications, modulation, digital comes there. This is the digital modulation APIs, set of APIs. So from here, you go to modulation, you bring down the Psk function. So this is the core. I mean, I'm doing in that sequence, of which it's actually more critical. I'm doing in that exact sequence. So the first function is modulate Psk. So in the modulate Psk, data has to come from elsewhere, so we'll not touch upon the data. But what are the other important parameters? We need two. One is the Psk system parameters. Next one is the filter coefficients. Okay. So again, you come back into this. You need to get these two functions. So what are those? This is your system parameter function, which I'll select as Psk. This is the first function, which you will be putting directly onto the Psk modulate function. Now from here, what all is needed in this function? We need the data from the modulation and filter parameters. This function that you see, this function is what has to give inputs towards this. So how do you retrieve that? Go to cluster, unbundle by name. So these are the functions these are the data points that are required, right? So what we need is modulation state. So just look at it from the perspective of what all is expected from this function, right? Modulation states, samples per symbol, okay? Pulse shaping filter data, which will go to the filter coefficient information. So over here, we need samples per symbol, which I'm wiring directly, okay? And then the modulation state. So I've designed this VA essentially. This is done. The next one is the generate filter coefficients function, which I'll bring here. The input towards that pulse shaping filter coefficients is wired over here. So this one part is done, and your output from that, it has to come as a complex waveform, which is this. The one thing is amplitude scaling, so we'll see that later. We'll see that separately, but this is the crux of it. Now from the filter coefficients functions, what are the inputs required? What is the filter? Which filter do you want? Right. So this is the first input, which is the filter you want. Then you have inputs like samples per symbol for the filter, which is essentially the same samples per symbol that you have defined. So This is the one. And then this is the modulation type. We'll expand this further. Get the modulation type onto this. Okay. After this is done, this core part, whatever this is, this much, whatever you see, this part of the code is what kind of defines your core modulation. So what functions did we use? Recollecting, what functions did we use? We used the modulate function, we use the generate system parameters function, and then we use the filter function. So these were required as an input towards the these two are a required input towards the PSK modulate function. Now, once that is done, another critical aspect would be to look at the symbol rate. Now, what is the symbol rate? The symbol rate, as we can clearly see, is essentially your IQ rate, okay, scaled by the samples per symbol. Fair enough. What is IQ rate? What is IQ rate? IQ rate is essentially your samples per second. Correct? No, IQ rate is nothing else but the sampling rate. So if IQ rate is the sampling rate multiplied by samples per symbol, sorry, divided by samples per symbol would give you the symbol rate. So I'm taking this IQ rate in IQ rate data. Just pull this back a little further. IQ rate data, and I'm dividing that by the samples per symbol. Okay, so I'll use a divide function first. Getting a little cluttery, I know. Let's clean this up. Okay, this is the IQ rate. Divide the IQ rate by samples per symbol. That will give you the symbol rate. Define the symbol rate as well. Okay, so this piece is done. Now the expected additional input is the data set, which currently what I will do is I'll create a constant to this, create a control to this, sorry. For the purpose of creation of a sub VI, I'll create a input. So this is the data that would ideally be expected. This is the filter parameter input. So two inputs have to come to this function, and then your amplitude scaling is another aspect, which we'll see now. Essentially, what you need to do is to kind of create a complex waveform. So this much, this part is what you need to develop. Okay, so once again, inputs, what are the inputs? Number of modulation states is 4. And then what you have is the differential PSK, you can enable it. Then you have the samples per symbol, which is directly obtained from the end user, from the UI. IQ rate scaled by divided by the samples per symbol would give you the symbol rate. Okay, and once this is done, you can actually create a subway out of this. I'll not go there now. You guys can do this development. Do till here, and then we will go to the. We'll go ahead and make a subway out of it. So I'll take 5 minutes. Again, I'll give you 5 minutes. You can go through this, and then let me know once you're done, please. This is actually the most important part, guys. Whatever this part is, this is the core part. Then we have one more exercise. After that, we'll just bring in the functions from the exercise solution already given to you. This and the next one. So this is the modulation. Before that, we have the packet formation. Those two are the most critical ones. We will do only those. So please ensure you finish this. I mean, you actually spend time doing this development. Because at a higher level, when we speak, things sound easy or things sound trivial, but the moment you start the development, you will understand many intricacies and the core mathematics behind a system like this. If you have any questions, please bring them up. Okay. So now to make a sub AI, how do you do it? We had discussed this on the first day as an answer to someone's question. You select this portion of the code. So whatever is a portion of the code you want to be in the sub function, you select that piece of the code. Okay. You select that much piece of the code. Go to edit. Okay. Go to edit and say create sub AI. So I've created the sub AI now. So this sub AI, this particular sub function is capable of getting an input data stream and the modulation filter parameters and giving the complex waveform out. Just to take things ahead a little fast, I'm going to reuse the function on IQ padding from here directly. This is the IQ padding function. This is there in the main exercise that you have been, the solution that you've been given. So you'll use that. That is okay, completely fine. So this is the IQ padding. Okay, IQ padding is nothing. I mean, I'm just showing you the functionality once for discussion perspective. Once more, so simple. You're getting the data. Pay attention here. You're getting the data. Okay, retrieving the array. Depending on the array size, total number of elements, which is essentially the size of the complex array that you are created right now, you have a padding ratio, and depending on that padding ratio, you are creating a new array, which you are appending at the beginning and at the end of the complex array that you have already. So that's it. That's the functionality. Finally, again, same output complex waveform coming out. So that part is done. This is that part, and then just to see what is it size of the total array, I'm using a I'm retrieving the y array, bringing it to the size. So this is an array size function that lets me find out the size of the total total elements in the array that is being generated. Okay, fair enough. Now the output complex waveform, it is not really a required data to be displayed, so I'll delete that. I'll bring it to this pipeline. This pipeline is essentially supposed to bring the data from here towards this. This is not like nothing related to RF. This is just an optimization technique in case it has not been covered before. It's just an optimization technique, which is called pipelining. After this optimization technique is done, okay, after it is done, this is brought directly towards the constellation graph, and pay attention, this exact same data is what goes towards the Usrp, right? Fair enough. So this is the first set of activities to be done. Now following this is the modulation. Okay, this way does the modulation. What is before modulation? Packet formation. So we'll go to the packet formation part. In the packet formation, again, what are the most critical parameters? In the packet formation, you have a set of frame parameters that you've been asked to work with. Okay, so this frame parameters, which is essentially the number of guard bits and number of sync bits, is all you need to work with. So for that, you will use some array functions. Okay, so how do you do that? You bring it here again. This is, we will build this here, and then we will bring it up to the we will try and make it into a proper sub vi, and then pad, like bring the other VIs also into the same function. So how do you do this? Again, you need to retrieve the elements from this guy, frame parameters. What are the two frame parameters you need to work with? One is guard and sync. Only these two are there. Only these two are there. So now from here, what you need to do is you need to make an array, which is using the initialize array function. The array size, so number of guard bits. What data do you want? What element do you want? You need a numeric of what type? This function, right? This function, the modulate function, it actually expects an I8. So I'll change the representation towards I8, and I will make this 1. Okay. Now you have created the guard bits. Now you need to create the sync bits. How do you create the sync bits? You could use the PN order sequence function. utilities. Using the search functionality. This is the one. Okay, the generation of bits. This one will create a sync bit sequence. So the sync bit sequence, not defining anything else other than the number of sync bits. The sequence, everything will be taken by default. We can continue using that. And this is the output bit stream. So now we have created the guard bits, sync bits. Now what do we need? The most important one is the actual data. So this is where the data is coming from. Okay. So essentially what you want to work with is kind of a array function which builds an array that has 4 components, right? Because now you're looking at merging the guard bits, sync bits, and the input data stream. So first the guard bit, then the sync bit, then the data bit sequence, and finally the guard bit again. So what do you have here? We have made an array of all these elements, and this instead of the input bit stream, the padded one, the actual packet is being transferred towards the function here. So this is the packet formation. Okay. So now the packet formation is ready. These are my functions that are required for the packet formation. So this part I'll select and I'll say edit, create a sub VI. Okay. You can do this part. You can do this much. Again, 5 minutes. No, my mic is not muted. I'm audible to everyone, right? Mr. Shyam?
Yes, you are audible perfectly.
Okay. Mr. Shyam, I think it's a local issue. Please check on that. Yeah, so this is the core part. This is the core part of the packet formation. So what we have done now, this is the IQ padding, this is the modulation, this is the packet formation. So you can proceed with developing this, taking 5 minutes. Like I said, icon editing, etc., is something that you can take up on your own time. Just it's simple. I mean, you just right click and say edit icon. You can bring it like it looks over here. This is very similar to paint. You just select edit. This is essentially paint only. So I'm not going to cover this. in the session, but you can try it out yourself. Okay, the code, whatever the subway that we created now, it looks like this. So they have the bit stream, parameters, output complex waveform. Okay, so how do you make a subway again? Select this part, select only this part. Go to, okay, bring this here to avoid clutter. Select this part and then say edit, create subway. So now we have the two most critical functions in place. Okay, then what you can do is, for the interest of time, the simple function that you need to use that is available, you can use a quick drop. All you need to do is you need a function which is taken from here to generate the bit stream, which is essentially string to byte array. I'm converting the string towards the ASCII code. So this is my message text. This is my byte array. I'm going to use this only. Okay, this is my byte array. I will use this. Then now I'll bring in the other functions that are there already in the other program. So what do you have? Just move this up. So what do you have? You have bytes to bits, which is again a very simple function. All we are doing is we are taking these bytes, then converting these one by one towards Boolean data, and then corresponding to that Boolean, you are taking an I8 integer data. All I'm doing is I'm putting it as 1 and 0. That's it. Okay. So have the data here. This is my bit array. The numeric one is what you want. Then what you are doing is there is a Gole encoder, so you can directly use that. This is a Gole encoder. Okay. And you bring it to this. Adding ratio, you bring here. So the first one, okay, even if it will give a hardware error, just to show you the data set, what I will do is I'll remove this pipelining and I'll wire this directly just to show you how the data appears or the constellation actually gets in. Okay. If I, let's say, set the modulation type, PSK, IQ rate, gain, all the points are set. I run the code now. Let me use a root raise cosine shift filter. This will throw an error because it will not work because I don't have the hardware connected here, but you can see whatever we have developed, it is actually giving us a proper constellation. And this data, as you see, it would be in a format. And just to display again, I'll create an indicator here for you to see. This is the waveform. This is the actual waveform. And you can see that there is data in this array, this entire array. There is data points. I'm just going through this array, and you can notice that the data points, this is the initial padding. You notice this is the initial padding, as you see. Just try to unlock this. Retrieve the elements through the unbundle function itself. So you can see this is your data value. As the transition happens, you can notice initially it's 0 padded. Then as I'm moving down, this is where the transition is happening. And the transition happens, okay, you can actually notice stable values, which are essentially your points on the constellation, actual data points on the constellation. And then you're again going to transition. Then you will see the stable set of values over here. Then again the transition. Okay, so this is how the complex waveform would be, which is what you see on the constellation graph also, right? So let's go back to the original example. So this is the demo PC. Over here you can see these are the functions that will be used. 5 functions. First one is, what is the first one? The first function is bytes to bit. Okay, the first function, it's in a very simplistic manner, you're converting the message, the text towards the byte array. Then you're converting the bytes to bits. So we'll go by that. Convert the bytes to bits. Then you have the Boolean encoding. Then you have the bits to frame, which is the frame structuring. Then you have the frame to IQ data, which is actually the modulation. And finally, you have the IQ padding, which is padding the data set with zeros in the beginning and the end. Okay, and then you're pushing this data over towards the Usrp and the constellation graph or display. So I'll run the code once more. The transmitter and the receiver, I'll just reinitialize everything. I'll run the code. You can notice that I'm receiving the data as it is transmitted, and you can notice the packets. These are the packets that I'm getting, out of which one packet is getting isolated. And the study on how the receiver is implemented will be done in the afternoon. It's slightly more complicated, but essentially here also you're extracting a frame, demodulating, decoding, converting the bits to bytes, and then finally bytes to message. So the extraction of, there are techniques in the demodulation to kind of do the synchronization or detect the synchronization, which you can see separately in the next session. Okay, I think I've overshot the time. If you have any questions, I can take it up. Any specific questions? Hope the flow was clear to you. Hope at least some of you are able to follow through along with me and are clear on the actual implementation part. If you have any questions, let us know. Let me know now. And the receiver part will be very clearly taken in the second half. Anyone, any questions? Yes, please be a little more responsive to the sessions. It really helps us also get a feedback into if you guys are able to get along or kind of be in track with the sessions and motivates us also. So please be a little more responsive. It's really helpful. Okay, Amit sir, are you there? Hello, Amit sir. Okay, looks like he's not available. Okay, so guys, the thing is, I'm wrapping up the session then. The next session is scheduled to be running at 3 o'clock. I don't know if there is something else internally planned for IIT Jammu participants, but the sessions from our side, the next one is at 3 o'clock. So please join. That would be the receiver design. If you have any questions regarding the transmitter that you are still trying to do and you want to try out, you can do it. So you can, if you are you just want to observe, then over here the exercise is what we were working on and the transmitter.vi is given. You can open that. You can just observe what is being done in the VI step by step. That is also perfectly fine. Okay, so if there are no questions, then I'll be signing off. Our next session is at 3 o'clock as far as I know. Meaning in the FDP, Guard's next session is at 3 o'clock. Please ensure you join back by then to see the receiver design. If you have any questions, please reach out to us. And yeah, hope everyone is safe. Stay safe. Take care. Bye. Thank you.
Okay, so thank you. We'll meet again at 3 p.m. Okay.
Thank you for 5 minutes and then we'll start. All right. It's been 5 minutes. If any of you have people you know will be joining, you can message them. That session is now starting. Can anyone here tell me if I should wait for some more time, or can we start? All right. Can someone just unmute and tell me if I'm audible or not? All right. Thank you, Mr. Thama. All right. Okay. I understand that it's the afternoon session, and I mean, it might be slightly difficult, but it will be really helpful if you guys can like speak in between. I will try to not make it super boring. There are a few very interesting concepts that I'll try to cover today. As for the agenda of the session, I will be taking you through. So I'm assuming that in the first half of the day today, Nilutpal and Amal would have covered parts of a packet transceiver in the class, right? Now they would have focused mostly on the transmit side of things. My session here, this session from 3 to 5, will be focused more on the receive side of things. Let me share my screen. Right. Is my okay? One second. Right. Is the screen visible to all of you? And could someone tell me if you're able to see the presentation? I see. All right. Thank you. Right. So this particular section is called receiver algorithms for a packet transceiver. And what I'll be doing is taking you through this block diagram, what you see in front of you. Now, what I have with me in terms of hardware is, I think, something that you would have already seen in the day. I have the standard packet transceiver code, which is running on a remote system. It has a USRP, which is acquiring RF data at a certain frequency, and we are processing that RF data to finally extract text out of it, text which we had transmitted from the transmit side of the code. There are a lot of steps in between, some of them really basic, for example, converting bits to text. Some of them really interesting, which I think if we have undergraduate students with us today, you would have learned in information theory. There are steps like channel coding, etc. So I'll really like if I can get some nice inputs from you all on that. And some of them really, I won't say niche, but some things which we don't typically think about when we are just studying, but they're really interesting and impactful algorithms. So I'll go through each of these blocks one by one. I'll try to explain the theory, and then I will try to explain how this has been implemented in, or how to implement this in LabVIEW. The result, I'm again assuming you have already all seen, okay? If there is anyone who has something to add to this agenda or something, you can please tell now. In between my presentation, if there are any questions, please feel free to stop me at any point in time. Also, for people who were there in my session yesterday, I had asked a couple of questions. One was trying to see if you can figure out the IQ data for FM modulation, frequency modulation. And the other one was to try and find out why, when we are doing complex sampling, the sampling rate, the IQ rate, doesn't have to follow Nyquist criteria. So if anyone has come up with answers for that, would like to discuss that, this session is a good time to do that as well, right? Okay, perfect. So let's now go ahead. So the first things first, and I want someone to answer when I'm trying to acquire RX data, when I'm trying to acquire data through USRP. Yesterday we had gone through an example code. What were some of the very basic parameters that I was setting on that example code on the front panel? to give you an example, I would say center frequency. Can someone else just quote a couple of more parameters? If you are not willing to unmute and tell, you can write in the chat window, that works as well. Anyone, you might remember something like we used to set the IQ rate, the active antennas, etc. Right? All right. Okay. See no one responding, so I'll just move ahead with the explanation portion. So the first stage that that I want to talk to you about is called data acquisition, which implies that, which is pretty much what we have been studying since yesterday, at least what I taught all of you yesterday, that we are now trying to acquire data and we are trying to demodulate it to text, which means that first of all, we have to figure out how do we, or how rather, let me say, how much data do we acquire? Now you have to remember this is a packet transceiver, which implies that you do not have data coming in as a continuous stream like yesterday. You don't have two sine waves which are modulated, right? And then there is a silence, RF silence, and then there is a burst. So you need to first of all figure out how much data do you want to acquire, which you will further do your demodulation on. So for that, we follow a small algorithm, and I want someone on call, if possible, to just keep answering if I ask any questions along the lines of this algorithm. The first thing we do is we find the total number of bits to be captured. If you were sitting in the morning session, can someone please tell me how will I find out the number of bits to be captured for acquiring one packet? What will it depend on? Anyone? Size of the file. All right. So let us assume here, let me put out the scenario. We will be writing a text message. Let us say I'm writing the lyrics of a song in a text box on the transmit side. Okay. So now the receiver typically doesn't know the message, or else there'll be no point in transmission, right? There'll be no point of building a packet transceiver. But one thing which the receiver does know is the packet structure. Okay. So to find out the total number of bits to be captured, if I want to capture one full packet, I definitely need to know the packet structure. And if you guys would have heard this in the morning also, that typically on transmitter, we implement something called channel coding. Can someone on call quickly just write on the text on the chat window for everyone, or just unmute and tell me, what do you think will why do you think will channel coding have an effect on the total number of bits that I want to capture? If I know the packet structure, beyond that, why do I also need to know the type of channel coding to find the total number of bits? All right. I don't see any answers. So any which ways, typically channel coding is the process where we are adding redundant bits, right? The reason we are adding redundant bits is so that we can counter any kind of channel errors, we can detect them at the receiver and even try to correct them at the receiver. So to find the total number of bits to be captured, first of all, we need to know the packet structure at the receiver, and we need to know the kind of channel coding scheme. Once I have the total number of bits, the next step is to use the PSK format to find the total number of symbols. Once again, a question. If you know the PSK format, let me say that the PSK format is BPSK, and I want to capture 250 bits. Then how many symbols am I trying to capture? Can someone just give me a number? Mod scheme is BPSK, so mod scheme is BPSK, number of bits is 250 in a packet. So in a packet, how many symbols will I be trying to capture? Remember, it's BPSK. $125. Okay. So you are saying 125, which means that you are saying that I will have one symbol representing 2 bits. Ben, is that right? Isn't that typical, something we typically do when we are working with, let us say, QPSK? On the contrary, if we have BPSK, we typically have one symbol being represented by a single bit. So you have 0 being given 1 IQ value and you have 1 being given 1 IQ value, right? Which implies that when we are working with a certain PSK format, and if we have the total number of bits to be captured, we will find out log base 2 of that PSK format, and then we will divide the total number of bits by that result. That will give us the total number of samples to be captured, right? Now, finally, yesterday I talked about something called samples per symbol, and even in the morning you would have talked about this. So samples per symbol means how many analog samples will be used to represent one of these symbols that I'm talking about. So if I know that the number of samples per symbol is, let us take a variable capital L, then I can tell that the total number of samples that I would like to capture in order to capture one full packet would become number of bits divided by log 2 m into L, right? So we will capture this data, we will capture these many samples, and we will then display them, the raw constellation as well as the eye diagram on the code. To give you an idea, this is how the algorithm broadly looks like. You know the packet structure, which you will be able to see over here. You know the packet structure, which you will be able to see over here. So you will know how many data bits are there, how many other training bits are there, sync bits are there, guard bits are there, etc. After that, you know the number of bits that have to be added because you are using some kind of channel coding. If it's Hamming codes, you can use the rate to find out the number of redundant bits. Rate is in turn inversely proportional to it's also proportional to the order. So if you know the order of the Hamming code that you've used at the transmit side, you can find the number of additional bits. And you can also use the PSK type, which means that if you're using BPSK, then you will have the same number of bits as the number of symbols. If you're using QPSK, the number of bits, the number of symbols will become half, so on and so forth. If you're using 8PSK, the number of symbols will become divided by 3, like that. Now, once you have the number of symbols, you're going to multiply it by samples per symbol. So if someone wants to do a quick unitary method, you can do that and check. That the resultant I will get will be the number of samples I need to capture in order to capture one full packet faithfully. And that we will supply to the Usrp, which will then go ahead and capture that much data and give it to me. Okay. I hope this part is clear. If anyone has a question, please ask. All right. We'll move on to the next one. Right. We'll move on to the next slide. The next thing that we do with this data that we've just received is we implement a matched filter. Right. Now, what is the point of implementing a matched filter? Can someone in a very brief single sentence tell me why do I need to implement a matched filter? General communication doesn't even have to be specific to this. When do we, why or when do we implement a matched filter? All right, no worries. So typically matched filter is a linear time invariant filter whose impulse response is folded and conjugated version of the incoming pulse shape without noise. Now, this implies that matched filter is typically implemented to invert the effects of a pulse shaping filter. Now, all of us on call, and I think all of you know better than me, that a pulse shaping filter is required to be used when we want to reduce the ISI. Right. So because we are using a pulse shaping filter, one of the reasons. Now, because we're using a pulse shaping filter on the transmit side, corresponding to that, we need to use the matched filter on the receive side. All right. Now, now that we know why we need to use a matched filter, the question becomes, how do we match filter the incoming waveform? The process to do that is simple, straightforward. You generate filter coefficients, and these filter coefficients are generated based on some particular parameters. For example, here, the code that we have built, the code that I'm showing you, assumes that the type of filter is fixed at root raised cosine. So it's an RRC filter. Some other parameters which will be used will be the filter length and of course the filter parameter, the alpha value, right, which controls the roll off. Once you have these values, you can either use your own MATLAB code, you can use your own C code, you can use your own any other Python code, anything, or you can use a modulation toolkit VI, or you can use pure LabVIEW logic to come out with filter coefficients. Now, once you have these filter coefficients, applying a matched filter is as simple as convolving this with the incoming signal. All right. So now at this stage, at the end of this stage, we have captured the amount of data which would be equal to one packet, and we have match filtered that received waveform. Okay. Now, what will be the next stage? Can someone take a guess, or would someone like to contribute? What will be the next stage? Anyone? Demodulation, correct. Demodulation will also come, but it will come after 2 stages. Now, as I said in the beginning of this session, there are some really interesting algorithms which are typically implemented in this digital communication, which we don't read up a lot about when we are doing our theory, right? Now, one of these very interesting algorithms is called symbol timing correction or symbol offset correction. Okay. To understand why or when do we do symbol timing or offset correction, you need to understand the need for it first. Okay. Now, typically speaking, in older times, not typically speaking, rather there are some situations where you have a transmitter and receiver, both of them running their own oscillators, right? Now, the oscillator at the transmitter and the oscillator at the receiver are typically independent. There are scenarios where you can transmit the clock along with your signal from the transmitter to the receiver. And there are scenarios where you can have the receiver being in sync with the transmitter clock. This can be done through a voltage controlled oscillator, right? Now, both of these mechanisms are good because they achieve perfect synchronization between the transmit LO and the receive LO. But this is not always the case. As a matter of fact, typically you will need to account for these errors without getting a chance to match these two oscillators, okay? And the way to account for these errors in this kind of a scenario, in a digital scenario, is called symbol timing or symbol offset correction. Okay. Now, if you're able to look at the illustration I have on the right side of the screen, you will see that there are 3 waveforms that have been drawn. Remember that the shape of these waveforms looks like a sync pulse. That's because these are coming out of a RRC filter. So that's the shape that they're actually representing. Okay. Now, what are these 3 waveforms? These 3 waveforms are nothing but waveforms corresponding to, let us say, symbol 1, 2, and 3 at the transmitter, right? Now, if you remember the theory behind a pulse shaping filter, you will remember that the reason why we use RRC as a pulse shaping filter is because the peak of one of the symbols always lies at the null point of its preceding symbol and its next symbol, right? Because of which, if you notice that the first symbol has a null over here, has a null here, null here. So all 3 symbols have nulls at the same point. But the first symbol's peak point occurs over here, whereas the second and third symbol are null at this point, right? Similarly, the second symbol's peak occurs at a point where the other 2 symbols are at their respective nulls, which means that ideally, if I would want to capture this data, I will just take all the data points occurring at this vertical line, or I can take them at this vertical line, all the dotted lines, right? Or this line, this line, this line, so on, so forth, correct? But now what happens is, ideally, these symbol boundaries, as you can see in the diagram, are where I would want to carry out my sampling. But more often than not, your receiver will have some amount of delay with respect to the transmitter's clock, which means that there will be some delta offset between where the receiver will actually sample and where the receiver should have sampled. That delta offset is called a symbol timing offset or a symbol offset. Okay. Now, as we know that in case of an RRC, the maximum amplitude is achieved at the ideal time of sampling, which means that if I ideally want to capture a sample for this particular symbol, the first symbol, I should be capturing this sample, right? Another advantage of capturing this sample is that when I try to capture at this vertical line, I will actually be taking nulls on all the other symbols. So I will also avoid interference from any other symbols. But what happens? Look at the gray area which has been highlighted. Because the receiver is not in exact phase lock with the transmitter, its clock may be slightly offsetted, which means that instead of capturing at this dotted line, it is capturing slightly before the next one. Now, if you notice, if I capture at this dotted line slightly before the next one, the one that is highlighted in gray, I will not get the appropriate sample value for the first symbol. And also the value that I get will actually have a lot of interference from adjacent symbols, right? Now, in order to make sure that I always capture the correct symbol values, right? Can someone tell me what do you think we can possibly do? What is one thing which is very obvious when it comes to this image, which will happen if I'm capturing at the right moment? In this image, you can see that the amplitude of the samples pertaining to a symbol are varying in time for all the symbols, right? And they're all being transmitted together. So can you think and tell me what is one property which I can very easily use to distinguish between the correct sample and an incorrect sample? Anyone? Nyquist rate, okay. Any other answers? Now, Nyquist rate would typically mean that you are thinking of sampling at a higher rate, right? But over here, that is not our concern. Over here, our concern is when do we start sampling? Okay. So if you notice, and thank you for that answer, Swati, sampling in the null points. Okay. So you're saying sampling in the null points, right? In a manner of saying you're right, Ben. So here we have one of these samples for every symbol being at its max when all the other samples are at null. So if we sample at this max instant, right? If we sample at this max instant, this one followed by this one, followed by this one, then we would have actually achieved perfect synchronization with the transmit clock, right? Now the catch, here is the catch. I don't know when the receiver is going to start sampling. I only tell the receiver, boss, you start sampling, and as Swati said on chat, start sampling at Nyquist rate or at a high rate, right? Now the receiver has given me a ton of samples, right? I need to figure out which is, I need to process these samples in a fashion such that I can align the receiver clock with the transmit clock. So think of each of these blue pointers as one sample point, right? And think of, can someone think of an algorithm by which I can actually align these sample points with each other? Can you see that if I assume one of these points as the starting point, decimate the signal, and then add the powers, I will get the maximum net power only if I'm sampling at these vertical lines, right? Because if I'm sampling at other vertical lines, I will typically get one of these samples. I will not get this particular high valued sample. Okay. Now, following the same logic, typically, when we want to do symbol offset correction, we take the incident waveform. The incident waveform is already a collection of sample points, right? We start with the first sample and we decimate the waveform. What do I mean by decimating? I pick out every, let us say, 8th sample, because we are doing 8 samples per symbol, let's assume. So I pick out every 8th sample from that waveform, starting from the first sample, and I find out the total power contained in this decimated waveform. I run another iteration where this time, instead of starting from the first sample, I start from the second sample and I calculate the same power value. I do this repeatedly And I will need to do this how many times? If someone wants to answer, how many times will I need to repeat this algorithm to arrive at which is the optimum sampling point? Perfect. So number of samples per symbol, which means that think of it like this. I have, let us say 4 symbols that I'm transmitting, and my number of samples per symbol is 8, which means I'm transmitting 32 samples. Now I know that in these 32 samples, there are exactly 4 samples which represent my signal in its best form. So what will I do? I will first start with the first sample, maybe the 9th sample, the 17th sample, so on and so forth, right? And with that, I will try to find out, okay, with these 4 samples, what is the net power that I have? I will store it in an array. Then I will start with the second sample. I will take the second sample, 10th sample, 18th sample, 26th sample, so on and so forth. I will find the RF power contained when these 4 samples are taken as the, the requisite samples. Similarly, I will continue doing that till I've reached the 8th sample, right? Now, once I've reached this 8th sample, I have an array full of power values, 8 of these power values, and I will find the max of these power values. Once I have the maximum of that power value, I will find out which index that is occurring at, and that will be the correct symbol offset. Okay. So for example, if I'm talking about this particular case, then I will have 1, 2, 3, 4, 5, 6, 7, 8. Let us say that I've started sampling over here at this instant. Then I will first capture all the, I will first calculate the RF power from the waveform when it is captured at samples starting here, then here, then here, then here. I will realize that when I come to the 4th sample, I get the maximum power, and hence I will know that my symbol offset correction is 4. Okay. So like that, we implement symbol offset correction. The LabVIEW diagram is also shown over here in the same page. And if you can notice, we take the incoming waveform Y, and we take the number of samples per symbol, and then we are choosing through this particular block. It's called index array block. We are choosing every 8th sample. We are finding the magnitude of every 8th sample, finding the power by squaring, adding, and then finding the maximum or minimum of this array to find the symbol offset. Okay. This is an extremely important concept of a wireless link. If you have read about eye diagrams in your course, then eye diagrams are also very helpful in finding the optimum sampling point. So,
Shubham, there is one small question maybe. So similar type of data acquisition model is also applicable for HackerF1 or maybe simple RTL STR as well?
when you say sampling model, what do you mean, sir?
I asked similar kind of data acquisition model. Is it applicable for HackerF1 software defined radio as well as RTL STR?
Absolutely.
Is it the same, or for them they are different?
So I don't work with them very actively, but as far as my understanding of software-defined radios go, their architecture is pretty much the same. And because all the algorithms that we are implementing are happening after acquisition has happened. So I think, sir, the way in which I am doing acquisition here will remain the same on those SDRs as well. Should remain the same.
Okay.
And as long as the algorithms...
mark your attendance as well.
Sorry?
No, I am requesting attendees to mark your attendance as well.
All right. All right. So yes, so this is what we have for symbol offset correction. Okay. I hope this is clear. If there are any questions, please feel free to ask. Now, once you're done with symbol offset correction, can someone again think of what will be the next step when we move ahead in our receiving chain? See, if you are trying to understand how this goes, I really recommend having a mental picture. Okay. First of all, we took a ton of data. Okay, we don't know what is inside that data. We just know that, okay, this data somehow relates to the packets that we are transmitting. So the first thing was, okay, boss, let's not take infinite amount of data. Let's only take the amount of data. Right. Sir, I think there is some kind of a concern with the attendance form. If you could respond to that. Right. So if we are taking, instead of taking a ton of data, we should only take the amount of data that corresponds to a single packet. The next step that we did was, okay, this data seems good, but let me find out the right starting point of this data. That's where we used symbol offset correction. Now that we've made sure that symbol offset correction has happened, what do we need to do? We of course need to downsample this data. Okay. Once again, since we had multiple samples per symbol, we first found out which is the right downsampling start point. And now that we found that with symbol offset correction, we downsample this data, and we do that by a factor of samples per symbol, which means that whatever is the number of upsampling factor you had on the transmit, we will keep the same downsampling factor on the receive, and we will find out the relevant samples only. Okay. If you're looking on the screen, that's what is written over there. Of the first step that you do to implement this step is offset the samples by the required amount. And second step is pick one in every L samples thereafter. For those of you who have also done a bit of LabVIEW or who've been studying LabVIEW for the last couple of days, you will be able to make sense of the block diagram that is given. You have a waveform which is coming. You extract the Y, which is the array of samples from that waveform. You send it into a loop, and within that loop, you are indexing. This is called index array. How are you indexing? You are taking the sample number, which is transmitted by this blue colored wire. Now, this blue colored wire is giving you samples following the formula I into samples per symbol L plus offset O, IL plus O. Now, this O value is fixed because this tells about the initial offset. I is going to change per iteration starting from 0, and L is the number of samples you choose. So in every iteration from the incoming waveform, you will pick up the IL plus Oth sample. Once again, build it into an array and give the final downsampled waveform. All right. So now, once again, let's go back to our mental picture. What do we have so far? We had a lot of samples. Now we have fewer number of samples, which most probably correspond to some kind of packet, right? So far, we are sure that this corresponds to some kind of packet, but we don't know where in this samples that we've acquired, the packet begins. The packet might begin halfway in the acquired sample set. It might begin at the very first sample, or it might have begun already. It might end within this acquired data set, right? So the next thing is that we need to figure out what is the start point, this time not of the samples, but rather of the symbols. Okay. For that, we do something called frame detection and synchronization. Right. Now, frame detection and synchronization is important again because there can be a lot of junk data. There can be a lot of junk data before the actual start of the packet. If you send all this junk data to your demodulator will end up generating bits which were never present in the original message. You will get a lot of bit error rate, and that is something no one wants. So the next thing that we do is we do frame detection and synchronization. So how do we do it? We need to detect the start of the frame. Now, to detect the start of a frame, we need some kind of an indicator, right? For those of us who work with microcontrollers, Arduinos or Atmegas, you will know about start bit, stop bit. For those of us who've read about UART and SPI and all these serial protocols, you will also know that there is typically a concept where you explicitly call out a start bit and a stop bit. The intention behind calling out a start bit and a stop bit is the same. You want to indicate the start of a message and a stop of a message. There is also a parity bit to tell about the correctness of the message. Now, similar to that, when we are talking about packet transmission in RF, you have to realize the message itself consists of a lot of bits. So you can't have start bit as one. As a matter of fact, it doesn't make sense to have a single start bit. So what do we do instead? We have something called the sync sequence. We have a really long sequence of bits the probability of that sequence repeating within the data set is really low. That's how that sequence is typically constructed. And we attach that sequence on the transmit side. I think this is something that Nilutpal would have covered in the morning. We attach that sequence on the transmit side along with the data bits, right? This combined, this composite message of data bits plus that sequence is what we transmit. And because we transmitted that, at the receive side, we have a very simple method of finding out where the packet begins. We do that by using cross correlation. Okay. Now, would someone like to think of a way in which we can do this? It's practically written on the screen, but still, would someone like to, take a guess as to what is happening in the LabVIEW code? Or if not that, then can someone explain what cross correlation is? Anyone on the call? All right. I don't see any answers as such. Okay, so we can think of correlation between two variables. Okay, thank you. Correlation between two variables is correct. Now, in this case, the two variables that we are talking about, or the two data sets that we are talking about, are the sync sequence and Y, which is the received waveform, right? Now, when will the correlation be high and when will the correlation be low? When will the value of this correlation constant be high and low? Typically, whenever there is a match between the two variables in question, we have a higher correlation. The way in which we use this concept when we are talking about frame detection and synchronization is by realizing that if we take the sync sequence and in a sliding fashion, we run it across the received data, we will have a maximum correlation occurring at the point where the sync sequence is present in the received waveform, right? Once we do that, once we have found out this max sync value, we not only know that the packet is present inside the received waveform, we also know when the packet starts or where the packet starts. Okay. So this is the section where finally we will give an output of sync position. Okay. So once again, let me paint that mental picture for you. We had acquired a lot of data, which was pertinent to our message based on the packet size. After that, we had done symbol offset correction to ensure that we are sampling at the optimum time. We have the right start time when it comes to samples. After that, we had done downsampling to make sure that we now have the correct symbols with us. We have gotten rid of the extra samples. After downsampling, we realized that, okay, boss, now we do have a lot of symbols, but which in these are the relevant symbols, for which we did a correlation with the sync sequence, which was originally transmitted along with the message. And the resultant of that correlation gave us the value where the sync sequence will begin. So now we have a packet and we know where in that packet our message is beginning. Okay. Now, ideally speaking, the next step should be very straightforward, right? The next step should simply be that, okay, boss, you found out everything. You can go ahead and start demodulating the data, because now you know where the packet is beginning, you know the amount of bits you have anyways, and you know the modulation scheme. So you know the number of symbols you have. Just take those symbols and start demodulating the data. Can someone think a non-communication, a very logical reason why this might create a problem, why this kind of an approach can create a problem? When I say this kind of an approach, I mean that you have acquired, let us say 15,000 samples, or let me pick a better number. Let us say you have acquired 8,000 samples. When you know that you are using BPSK, and just as an example, assume that your message has 8,000 bits. Not 8,000 bits. Assume that your message has 1000 bits. Okay. Your message has 1000 bits. Your number of samples per symbol is 8. Your modulation scheme type is BPSK, and the number of samples you've acquired is exactly 8000. Okay. We've done everything. We've done symbol timing, offset correction. We know where the frame is beginning. We have sampled at the correct time. We know all this. But is there something which can still go wrong if I simply take this set of symbols which I have and start demodulating them? Okay, I will ask a yes or no question. Is it mandatory that when I transmit from the transmitter a packet, that whole packet from start to end will always be contained in one of this acquired data set, acquired waveform? See, it's a wireless transmission, which means that the receiver is continuously running and sending chunks of data back to the host PC. Is it a possibility? Please give me a yes or no answer. This should not be very difficult. Is it a possibility that in one of these waveforms, the entire packet is not contained? Instead, part of the packet is contained in one waveform and the part of the packet is contained in the next one. Is this possible? All right. Can you think of a way in which we can counter this situation? And it's perfectly fine. We are discussing algorithms. Algorithms come up on a daily basis in whatever we do, from figuring out the fastest way downstairs when you're rushing for a class to figuring out fastest way to connect to the internet when you're late for one. It's everything we do is algorithm. So can someone just unmute probably or tell, or anyone would want to share a possible algorithm by which we can make sure that we are not losing these packets which are scattered over waveforms? Okay. All right. Looks like no one wants to share, no problems. So, and just letting you know that like a lot of this session is dependent on interaction. So it'll be good if we interact. I will anyways continue going ahead, but the session will also get over fast, and it'll always be good. It's always good for learning if you all interact. So anyways, the next thing that is important and that we do in this receive algorithm is called packet parsing. Okay. Now look at the illustration on the screen. Look at the bottom side of the screen. Okay, let's read the text first. You can read the text. What it basically is saying is that since there may be a scenario where we have incomplete packets being sampled in iterations, we need to take care of the content spreading between two acquired waveforms and reassemble it in a way that we don't lose out on data, and we don't demodulate data which we should not have demodulated. Okay. Now, in the morning, you would have been told that the packets that we are working with have something called a packet structure, which means that first we'll have guard bits, sync bits, training sequence, then we will have the data bits which we actually need, followed by another set of another set of guard bits, right? Now, so this packet structure here, I've written it out as GSTPDFG. This is the packet structure that we are working with. One algorithm by which you can make sure that this overlapping of packets between two different waveforms doesn't create a problem when you're going for demodulation is by finding out the sync value. Now, here the assumption that we are going to make is that the packet transmissions happen on a regular basis. So once you found out the sync value, it will not, once you found out the symbol offset value and the sync position in the packet, it will not change drastically, right? Now, once you've made this, what you do is, instead of working with one single waveform, you work with two waveforms. You take the previous waveform, the waveform that is acquired, let us say in iteration number 9, and you take the waveform which was, let us say, acquired in iteration number 10 together. Over here in this illustration, the blue section represents waveform number 9 and the orange one represents waveform number 10. Now the green and the yellow sections correspond to the packets that are being transmitted over these waveforms and are being acquired, okay. Now, if you notice, the green packet is actually overlapped, or let me say it's actually broken when it comes to the acquired waveforms. The receiver has not been able to capture the green packet completely within one of its waveforms, it's spread over two. So what happens when we run our algorithm? Our algorithm comes here, it finds the sync value and it sees that, okay, boss, the sync position seems to be 4. But now, if my algorithm just takes this waveform and tries to acquire or tries to demodulate just this much data, the blue data, it will obviously be missing out on some important pieces of data which are being acquired in the next waveform, right? In order, there is a small algorithm which we do, which is instead of taking just waveform 9 data or iteration number 9's waveform data, we take both of these data and we club them. How do we club them? We take data after the sync position from the current waveform, and we club it with data up to the sync position in the next waveform. Okay, so instead of taking just 4, 5, 6, 7, we take 5, 6, 7, 1, 2, 3, 4. Okay. Now, when I say 5, 6, 7, 1, 2, 3, 4, this is basically the data which has been captured. Okay, you can see it over here. When I take 5, 6, 7, 1, 2, 3, 4, I will actually be capturing all the data that I wanted after the sync, and I will be capturing data up to the next waveform's sync position. Once I've done that, I know that the start of this capture is definitely going to be after sync, because that's what the sync position was all about. And I know that the total number of bits and hence the total number of symbols in my data is going to be how much. So I simply capture. So for example, I know that I only want TPDF. So I only want 4 of these units. I have gotten this whole big waveform together. I know that it starts at the right moment. The next step is super simple. Just take as many units as you want out of this combined waveform. So now instead of having 5, 6, 7, you are acquiring 5, 6, 7, 1. Okay. This way, you can actually make sure that you are not just taking packets and finding the right start time, you're also parsing them and making sure that even if data is getting overlapped between two waveforms, it's not creating a problem when you finally try to demodulate it. Okay. We'll take a minute here, and I want you all to just look at this code and try to see if you can make sense of what is happening when it comes to LabVIEW. Okay. This is the previous synchronized waveform. As I said, iteration 9's waveform. This is the current synchronized waveform, iteration 10's waveform. This is something called a delete from array, which basically divides this whole array into 2 portions, right? So in this case, what are we really doing? We are going to the sync position, and in the first case, we are taking data. Can someone tell me, are we taking data up to the sync position or from before the sync? I mean, from after the sync position? Look at this, maybe look at this illustration and try to tell. From the current waveform, we take data up to the sync position or after the sync position? Perfect. So we will take data after the sync position from the current waveform, and in the next waveform, we will take data before the sync position. That is what this section of the code is doing. This particular one is combining these 2 data points, and this particular one is finally extracting the meaningful part of the data, because as I said previously, we know the total number of symbols contained in a meaningful packet. Okay. So this is another interesting algorithm, which of course we will not read about in theory. But when you start developing these practical systems, you really need to figure out a lot of things on the go. Okay. Symbol timing recovery is one of those. It's actually a lot more formal and a lot more critical. Packet parsing is something which is a lot more specific to this case. Okay. So now let me go back to that mental picture. You had data, you got data equivalent to a packet out. You figured out the right start point. You discarded the bits before discarded the samples before that. You downsampled that data to get symbols. Further, you used all these symbols that you had acquired to now get packets. So now what you have with you is a set of symbols which you know for sure correspond to a packet. Correct? Now, what should be our next step? What do you think should be our next step? Anyone? Channel estimation. Okay. Why do I need channel estimation? That's a very good answer. Why do I need channel estimation? Ms. Swati, if you can just maybe briefly tell. Or anyone for that matter, if anyone would like to jump in and tell a bit about why do I need channel estimation? No one? To transmit the packet, correct. To solve the channel fading problem, correct. Which basically means that your channel is going to have some kind of an effect on your data. Now, you know that if your channel is going to degrade your data a lot, demodulation is going to be bad, because the data, instead of appearing close to your ideal constellation points, will appear at other random places. It might appear very close to the decision boundaries, and which would imply that you will get a lot of blur, etc. Right? So before we go ahead and demodulate this data, which is a very tempting step at this point, we definitely need to do channel estimation, followed by finding out the equalizer coefficients, and followed by equalizing this channel on the receiver, right? And that is indeed the next step that we do. That is indeed the next step that we do. We call this channel estimation and channel equalization, right? To repeat, we now need to remove the channel effects on the received waveform. This ensures that we get a cleaner waveform and also allows for better decision making at the demodulator. Now, as I mentioned, there will be 3 steps to this process. The first step is that we will find channel coefficients. Okay. Now, for finding channel coefficients, there are a lot of ways, there are a lot of algorithms that people use, but the algorithm that, for example, we have implemented in this code follows something called the CRLB theorem. If any of you is interested in any of these theoretical points that I touch and do not expand upon, please feel free to drop me a direct message. I can share the theory part with you, for example, for complex sampling or all that also. Or for example, in this case, the CRLB theorem. So we use the CRLB theorem where small h, as you can see on the screen, small h represents the channel estimate, and it is calculated with this formula. Now, what is A? A is the expected training data in a Toeplitz matrix form. Okay. So we take the expected training data. What is this expected training data? Now, just like we had the sync sequence being transmitted along with the data, we had another set of bits called the training bits, right? What is the job of these training bits? These training bits act as lab rats. Okay. Think of them as lab rats, think of them as pilot bits, whatever you want. We try to figure out what has happened to the data based on, or we try to figure out what would have happened to the data based on what has happened to the training bits. Okay. Which means that we have a certain set of training bits, let's call them small a. From those small a training bits, we find out the Toeplitz matrix, capital A, and we implement this particular formula. Now in this formula, as I said, H is the generated channel coefficients, the final result. Y is the received training sequence data, and A is the, as I said, expected training data. Now, once you do that, let me show you how over here. Okay. So just focus on the first diagram. You have incoming waveform, and this section, this particular sub VI is what is actually implementing this formula that I talked to you about. and the output that it is giving is the channel coefficients. Okay. Now, once we found these channel coefficients, the next thing that we want to do is we want to generate equalizer coefficients, right? Now, can someone tell me some common types of equalizers that are used in comms? Anyone? Any name you've heard of, any particular type you've heard of? Zero forcing equalizer, correct? MMSC equalizer, adaptive equalizers, perfect. So we have a lot of types of equalizers that are used, right? Now, again, every time that I come to this point, I keep telling you that in our code, because this is just one of the ways in which you can implement packet transceiver. So in this code, what we've done is we've implemented an MSC equalizer. Now, an MSC equalizer is useful because it doesn't actually increase a lot of noise. ZFE typically gives us some additional noise. A zero forcing equalizer gives us some additional noise. The very basic version of an equalizer is simply a matched filter, right? So we're not going there because we still have some noise. We want to remove the channel effects and we don't want more noise. So we are going to use an MSC equalizer. Now, how does this block work? Or rather, how does an MSC equalizer work? The MSC equalizer will try to find out equalizer coefficients while reducing the squared error. It is trying to reduce the mean squared error, correct? Now, to do that, we need to find the inverse of the channel coefficients, right? And typically in programming languages, if you all work with MATLAB, you would have come across a function called PINV, right? It's called, if anyone has used that function, you can just quickly type out what is the full form of that function or what does it do. Or if not that, then someone can probably tell me, how do we find the inverse of a matrix typically? What is one way of calculating inverse of a matrix, a commonly used way? Okay. Do you mean to say H Hermitian? Okay. So one very common way of finding out inverse is called pseudo inverse, and typically the Moore-Penrose pseudo inverse is what is very commonly used in programming languages. MATLAB also uses this very frequently. A lot of programming languages use this. Now, the Moore-Penrose pseudo inverse helps a lot if you're trying to find a solution to a set of equations where, of course, you don't know the exact solution, but you're trying to minimize the square error. Okay, so when you're trying to minimize, when you're trying to approach a least square error kind of a solution, the Moore-Penrose inverse way, rather I should call it, yeah, a way to calculate the inverse of an incoming matrix is a very commonly used and a very efficient way of finding out matrix inverses. Again, I wanted to look at the code written in front of step 2, and you will realize that is what is happening over here. We come in with the channel coefficients, right? This particular block is again creating a Toeplitz matrix out of those channel coefficients. And once we have that, we send it to this block. This is where we have implemented the logic for finding out inverse. Okay, this is where we have implemented the logic for finding out inverse of a matrix. And again, this gives out a matrix, but we only want the first row. That is what contains the equalizer coefficients. Okay. So once again, we were at a point where we knew we had everything we wanted to demodulate, but before that we realized, okay, we still need to remove the channel effects. So the way to do that is to do channel estimation and channel equalization. Channel estimation would start with finding out the channel coefficients, for which we used the CRLB algorithm. Once we had the channel coefficients, we found out the inverse of that channel coefficient matrix by using the Moore-Penrose pseudo inverse. And now what is the third step? So as simple as that, we simply need to equalize the channel. How do we do that? We convolve the incoming data with the equalizer coefficients that we have found out. Okay. Once we have convolved these two, the output that we get is the equalized waveform, the error corrected waveform. And I will try and run the code in a while, and I will try to show you the kind of difference that you will be able to see in constellations after you have done this step of equalization. Okay. I'm going to pause here for like 2 to 3 minutes just to see if anyone has any questions. I know sometimes it can be irritating if someone asks a lot to speak. I'm not pushing anyone, but if someone has questions, please feel free to unmute and ask, or you can ask on chat to everyone, or you can put a direct message to me. I will stop here for a couple of minutes. All right, I don't see questions. So we'll move on to the next step. Let me again bring us back to that mental picture. We got data, we match filtered it, we made sure we are starting sampling at the right moment, we made sure we've downsampled, we just have symbols. We made sure that after that we have symbols pertaining to one packet only. Once you've done that, we equalized those symbols to remove the effects of the channel. What will be the next step? Anyone? Exactly. The next step would be to do demodulation, right? Now, as I had explained yesterday in yesterday's session, you can always do demodulation using some inbuilt VIs which are available in LabVIEW. But here I'm trying to explain algorithms. So what we have implemented is something which is more mathematical, more so to say homegrown. Okay. So the concept of demodulation remains simple. We have implemented the most primitive form of, so to say, a decision boundary that you can imagine, where we are getting a received waveform. Okay. We already know that what the modulation type is going to be, right? So once we know that modulation type, we know what are the ideal constellation points. Now, the way to do demodulation is as simply to figure out what constellation point the received symbol corresponds to, and hence find out what bit that corresponds to. So what do? We take all the constellation points that we know are there, ideal constellation points. From each of these ideal constellation points, we subtract whatever symbol we have just received. Okay. Once we have done this, we find out the magnitudes of these differences, and we figure out which is the lowest magnitude, which would effectively imply which is the ideal constellation point closest to the received symbol. Okay. We already, once again, we know what bits or bit combinations have been allotted to these constellation points. So the next step is again as simple as that. We simply take these bits, we put them together, and what we achieve at the end is our combined bit stream. Okay. So congratulations, we started from acquiring very raw data over an antenna coming over the air from the Usrp. And now we have reached a point where we have most probably faithfully decoded data into bits. Okay. Now, what would the next step be? Once we have demodulated the data, we do now realize that so far when we talking about data, we were talking in terms of packets, and packets had a structure. If you would remember, there was a guard band, sync bits, training bits, maybe some kind of a preamble, maybe some kind of a frame. You have your data, you have your guard band, etc., etc., right? So now when we have gotten the bit stream out, we should always remember that bit stream corresponds only to a single packet. So now what do we need to do? We now need to do some kind of depacketization. Okay. Now, why do we need depacketization? It's written on the screen. We simply need to extract data from the packets. But one thing that we need to figure out, we have to make sure of, is that we have to make sure that we are maintaining order of the packets. Okay? You don't want sentence 2 coming before sentence 1. Now, to do that, one thing which we have already done is add the packet number, or let us say number every packet, and add that number to the beginning of the packet at the transmit end. Okay. So if we've already done that, it makes our job slightly easier, right? The way in which we approach this problem in LabVIEW is something I will explain to you via the code. So just bear with me for a minute. Let me share my screen and open the code. All right. Is my screen visible? Can someone tell me? Is my screen visible? Yes. Okay. Thank you. Right. So we are here. I will run you all through this code later. Any which way. So we are over here where we are now talking about sorting packets, right? So the first thing we do is that so in LabVIEW, you can run your code in parallel loops, and you can connect these loops via queues. So here we have this loop, which is doing all the DSP that we just talked about, and it is continuously feeding all the bits which constitute a packet into this third loop. Okay. So in this third loop, using this DQ, we are first taking packets and we are queuing them up. We are adding them up to make an array of packets. Okay. This is an array of packets. We decide on a number. Okay. Well, let us say 12. So the moment we have 12 packets done, okay, we have successfully retrieved the bits from the message corresponding to, let us say, 12 packets. What do? We said, okay, boss, buffer is now filled. Let us go to the next case, the sort packet stage. Okay. Now, in this sort packet case, what do we do? As simple as that, we sort. So every packet, the first element of every packet, we've arranged it in such a manner that it is the packet number. So we sort all the packets as per that packet number, and we give that value that, okay, was this is so and so packet ahead to this particular cable or this particular wire. Once again, for those of us who've been listening to the LabVIEW lectures, this wire, you can look at the color, it's a cluster. It's an array of clusters actually, wherein every individual cluster contains the packet number, the data stream, if there is some kind of zero padding, and also whether or not this is the last packet. Okay, so every element contains that. So this is how we are doing sorting of packets. We have this loop continuously acquiring bits and giving those bits for one packet each to this queue. This queue is emptied over here in the wait for buffer to fill stage. The packets are again constructed with some additional information along with the data stream. Based on that additional information, specifically the packet number, these packets are then sorted to make sure that we have all the packets in order. Okay, so this is the first part of depacketization. Let me come back to the presentation. Is my presentation visible now? Can someone just say yes or no? Thank you so much. Now, the last thing that we do over here, not the last, rather the last but one thing that we do over here with this data is called channel decoding. Again, I don't think that I need to tell people on this call what channel decoding is, but just to make sure that all of us are on the same page, whatever channel coding scheme we had used at the transmit, we simply need to do the inverse of that scheme on the receive side. Okay. Now, how do we do that? You might be seeing these two VIs over here. Okay. These are actually Modulation Toolkit VIs. The first one, this particular VI is called, this particular VI will basically do your Hamming decoding. Okay. And this one will do your Viterbi decoding, which will be used for convolutional channel coding. So if you have done convolutional channel codes, then this code will get activated. Okay. What will this do? This will ask you for the rate of code, the constraint length of the code, and based on that, it will obviously ask you for the input bit stream. And based on that, it will decode the stream and give you the original data bits that you had fed into the channel coder at transmit. Now, can someone on call, because again, this is something that I think all of us will be aware of, can someone on call tell me what is the rate of a channel coding system, or what is the relevance of rate over here? Right? Don't see any answers. Okay, I'm assuming that all of you know the relevance of rate. So again, this is when you're talking about convolutional codes. Similarly, when we are doing Hamming codes, when you have used Hamming codes to encode your data at the transmit side, you will again feed in your input bit stream to this code. You will see a lot of logic written here. The purpose of this logic is just to ensure that the number of bits that you are feeding to a Hamming decoder is a multiple of 2 to the power m minus 1, where m is your order. This is kind of specific, so you don't need to worry much about that, right? And in both of these cases, of course, we remove whatever zero padding we have done before we give the output. Okay, so we are now also done with channel decoding. Now, I think we are only left with the very last stage. Can someone just tell me what that last stage will be? Yep. So we are not doing scrambling because we hadn't done it on the transmit. And we have to remember that this is the stage, this is a packet transceiver, which means that we are trying to send a digital message. We have already at the transmitter converted it into an analog RF, acquired it, made it digital. Finally, we want to do something similar to source decoding. We can call it source decoding because it's a very arbitrary algorithm, arbitrary term. But what we are doing is very simple. We are simply taking our output bit stream, which is the bit stream which has been made after combining all these steps, the bits acquired from all these steps. We are going to reshape it, which means that we are going to convert that into blocks of 8. Okay. And then as simply, we are going to convert every block of 8 bits into a ASCII character. Okay. And that ASCII character, all those ASCII characters together will finally form the string, which is our message. All right. So just to quickly revise, we have a USRP, which is receiving data over the antenna wirelessly. This is something that yesterday I was asked in the class, that if I do over the air communication, what are some of the things I will need to take care of, right? So these are all the things that you need to take care of. So we will be receiving data on the USRP. We will be digitizing that data. We will tell the USRP how much data to acquire. We will then match filter that data to ensure that the effects of the pulse shaping filter are removed. We will then do something called symbol offset correction to make sure that we start or we find the right sampling point for the beginning. Then we will do frame detection and synchronization to make sure that we find the right symbol to start working from. Followed by that, something that is not shown here, but we will do packet parsing to then make sure that we have relevant data for packets put together. And then on each of these individual packets, we will do channel estimation followed by channel equalization. In this case, we have done estimation through a certain algorithm. You can choose a different algorithm. Equalization has been done using an MSE equalizer. You can choose a ZFE or any other equalizer. Once we are done with channel equalization, we will go ahead and do demodulation. Demodulated data will be depacketized, channel decoded, and finally, after source decoding, we will be able to construct the original text message which had been transmitted. Right? Are there any questions on this? Anyone? No? So let me now show you this thing in action. Can someone just tell me quickly if you're able to see my screen with the code? It's an AnyDesk screen with the code. Good. Thank you. Thank you, Ben. Right. So, and can someone also tell me if you've already seen this code today morning, or is it the first time you're seeing this? Was this code discussed in the morning? Have you seen this front panel in the morning? Yes or no? Already you have. Okay, thank you. Right. So then you will be aware of the various things that we can change on this front panel. Specifically speaking, you can, as we discussed, you can change the packet structure by choosing the number of guard sync, training sequence, etc. You can change the pulse shaping parameters, number of data bits, and channel coding. This is what I was just showing you, that depending on whether you're using Hamming code or convolutional code, there will be a slight difference in the way you code. Okay. You can obviously choose the USRP, IQ rate, carrier frequency, active antenna, so on and so forth. These are things that we had discussed yesterday. So I'm going to run the transmitter, followed by the receiver. Right. Now you'll be able to see that we are seeing the text on this received data text box on the right corner. Once again, to just make sure that we understand what is the relevance of all the steps that we just did, you see this RX constellation right now, right? It is twisted, which shows there is some kind of a phase issue. Thankfully, it's not rotating, which means that our carrier frequencies are relatively matched. But you will see that it's changing. The clouds are not that static. The constellation clouds are not that static, right? However, our received text is almost perfect. Doesn't look like there is even a single letter which is wrong or there is any kind of a bit error, correct? So all these things that we did before reaching to that place, before finally decoding, are all, or their importance can be seen over here. Let me auto scaling, right? Now you can compare the RX constellation and the equalized constellation. The equalized constellation is visibly more clear, and it definitely doesn't have that angle skew which is present in the original constellation, right? Again, here I am doing QPSK, but we can even go for a higher order modulation scheme. It will typically work without a problem. Sorry, excuse me. You can look at the packet number here and you will see that the packet number is constantly changing. Again, the transmitter has a large message. It divides that message down into packets and it sends those packets in a sequential fashion. The receiver keeps receiving those packets and displaying these packet numbers. But when it comes to reconstructing the message, it makes sure that all the packets are received in order and then their equivalent bits are combined or concatenated. Okay. Is there anything that any of us would like to try out on this, just to be clear with it, or just as an experiment? Is there anyone who has questions about this code? I will go to the block diagram and start explaining whatever I just explained in the presentation very briefly through the code itself. Is there anyone who has a question in the meanwhile? I'll wait for a couple of minutes. Right, we have a question. How is frequency and phase synchronization achieved in the scene? So in this particular case, so ideally speaking, if you're working with the DSP algorithms, you will need to implement some kind of an algorithm to do CFO correction. You will need to take care of carrier frequency offset by implementing algorithms. There are a lot of algorithms which do that. In our case, we are not doing that. We are not having to do that also because basically we are working on the same USRP board. The transmit and receive are connected to the same basic local oscillator, which means that the frequency variation is very minimal. That's why in this scheme it is not achieved, but in otherwise you might want to implement an additional CFO block. And as for phase, typically when you correct for symbol timing correction, when you correct for symbol offsets, you are making sure that the phase of the receive sampling clock and the phase of the transmit sampling clock are aligned. They are not really aligned, but at least when it comes to samples, the samples act as if they are aligned. So I think that is what is taking care of the phase improvement, the skew of the constellation getting better. Does that answer your question? We have we have functions which can also do CFO correction implemented. So if that's something that you're interested in, we can probably catch up later, and I can share some of those. All right, thank you. Any other questions? Right. If there are no more questions, I'd like to, okay, so maximum bit rate achieved through the scheme. Right. So, sir, right now we are working at an IQ rate of 200 kilohertz, and our samples per symbol is 16. So if I talk about QPSK, I mean, we can find out an estimate of the bit rate that we have right now by making use of these three things. So we have 2 bits per symbol and 2 samples per 16 samples per symbol. So you have around 200,000 divided by 16. I can quickly calculate that for you. So around 12.5K symbols per second. 12.5K symbols per second, and every symbol is going to contribute 2 bits because we are talking about QPSK. So it's around 25 kilobits per second currently. Now, as for maximum bit rate, sir, there are a few variables in this equation. Specifically, you can increase the IQ rate to a lot more. For example, the USRPs have a bandwidth of around 40 megahertz or even more. There are even 120 megahertz USRPs, which means that the IQ rate can go as high as 5M, 10M, a lot more, right? But then you will have to do this processing on FPGA. Keeping the scheme same, which means keeping the steps same, but moving the processing onto FPGA, you can increase your IQ rate by a lot. The moment you increase your IQ rate, as much as you increase your IQ rate, your bit rate will keep increasing. Another thing that is obvious is that you can change your modulation scheme. Right now it is QPSK, but as far as I know, if you're able to maintain appreciable power levels, then 8 PSK, even 16 PSK is typically doable. Okay. So the moment you go for 8 or 16 PSK, instead of multiplying by 2, you multiply by 3 or 4, as is theoretically, right? So that bit rate can actually go very high. There is not a particular number which I have for achieved through this scheme, but this can go pretty high. And worst case scenario, if there are some additional blocks that you need to add, for example, CFO correction, as I discussed, or something of those on those lines, then the bit rate can vary. Again, as an example, when it comes to 5G, you have some very specific schemes which have to be implemented, and those schemes are really hardware intensive. So you even have USRPs coming in which have those schemes hard coded into their FPGA architecture. So the rest of the algorithm that we discussed will still remain the same, and you can achieve bit rates which are really high with that. I hope that answers your question. Anyone else? Any other questions anyone has on SDRs before I get to explain the target? All right. As for the code of this, okay. So 3 questions. As for this particular code, I think we can put in a request with Nilutpal tomorrow when he takes the session. It's up to him if he can share this code, or will there be some conditions before that. Troubleshooting parameters that are there on the screen, Ben. So typically speaking, when you're working with so many loops, there are a lot of things you want to monitor to make sure that the data flow is happening properly. So this DSP loop count, decoding loop count, this is simply telling how many times the second and the third loop have run. This number of elements in Q1 and Q2, as I said, to transfer data between different queues, you need to use queues. These indicators talk about how many elements are present in that queue. This packet number talks about which packet is being decoded currently as of this moment, and whether or not that is the last packet in the original message being sent from the transmitter. Finally, this max sync value and current sync value, this is related to when we were trying to do frame detection and synchronization. Okay. So when we were doing frame synchronization, you remember we had the ideal sync bits and we had the received data, and we were trying to figure out that at what point, at what index do these ideal sync bits have maximum cross correlation with the received data. The value of that cross correlation, that max sync value, is what this is. And this is the current sync value. Like in this current packet, what is the sync value? And this is what is the max that has been received. Okay. Now, so as for FPGA programming, you want to know programming on FPGA will be different from this VI implementation or no? Okay. So programming on FPGA, right? Programming on FPGA will be slightly different from this VI implementation. Okay. There are 2 things, 2 places primarily where it will be different. Number 1, FPGA programming on LabVIEW happens in a graphical fashion, but there is a different set of rules that you are exercising under. So you use different loops, etc., right? So syntactically speaking, it will be pretty different, right? Now, when it comes to whether or not the algorithm will be the same. Whether the implementation in terms of algorithm will be the same or not, yes, the algorithms will remain pretty much the same, not exactly the same, pretty much the same. The reason they are slightly different on FPG, the algorithms, is because on host, I had explained the bucket and mug analogy yesterday for those of you who remember. So you know that there is a lot of water being filled into the bucket and we are extracting water in a mug. So you don't really have point by point access to data. Instead, you have access to batches of data. On the FPGA, on the contrary, all these algorithms will be implemented on a point-to-point level, okay? Which means that you will no longer work with 25,000 samples and try to figure out the correct 10,000 samples from that. No, every incoming sample you will be able to process at a very fast rate. To just give you an example, the loops here may be running at a few hertz, I mean, high value of hertz, but a few hertz. On an FPGA, typically these loops will run at a minimum of 40 megahertz, which means to process a single sample, process a single loop, you don't need more than 25 nanoseconds. So the VIs will be implemented differently because there you will have to do point-to-point implementation. Here you're doing array and matrix implementations. Algorithms will remain pretty much the same. And if you are concerned about, okay, then this means that we cannot use this at all, or you will have to start from the ground up when you're working with USRPs, FPGA, and LabVIEW to do packet transceiver. No, there is actually a library present on forums. It's called FPGA RF Comms Library 3.0. You can search for it. If you don't find it, just drop me a message, I'll share it with you. You can use that library, and that library actually has all the raw VIs you need for doing stuff like channel coding, for doing demodulation, for doing pulse shape filtering, match filtering, etc. Okay. Only the custom algorithms that I explained, the symbol timing offset correction and packet parsing, stuff like that is what you will have to implement on your own. Rest of it is already available on FPGA. Does that answer your question? I'm sorry it was a long answer, but does that answer your question, Mr. Arun? Right. Thank you so much. That's a really nice question. Thank you for that. Any other questions? Anyone? Please feel free. Right. So we'll probably spend the next 5 to 10 minutes just going through this code. We have already seen this code in detail, the individual blocks of this code. We have understood the algorithm behind them. We've understood the approach to them. We have seen how their LabVIEW codes look like. But now, just to get an idea of the overall flow of the code, we will go through the block diagram. Okay. Now, you will all remember from yesterday's session that these are the standard, the mandatory USRP APIs, which will always be there, right? Initialize, configure, initiate, read, write in a loop, stop, right? The same friends trip analogy that I had given yesterday. Now, apart from that, there are 3 loops in this code. The first loop is called the main receiver loop. The second one is the DSP loop. And the third one is your digital loop, which will basically do your channel, sorry, not channel. It will basically work with your digital messages. It will convert your bits to final message. The reason why we are using so many different loops is because the acquisition from the USRP happens at a faster rate as compared to the processing in the loops. And we cannot really have slower acquisition happening. So to make sure that all these work like, they work together and they can still work in different rates, we put these pieces of code in different loops and connect them using buffers. So the USRP will acquire a lot of data, but in bursts, it will keep filling up a buffer in burst. The second loop works in a relatively slow speed, but it works continuously. So it is continuously taking data out of that buffer. And similarly, the third loop will work at a different speed and will again be continuously taking data out of the buffer, which the second loop will be filling in. So what's the first thing that happens over here? We come to this loop. You see this thing called initial state. The initial state is called calculate frame size. So we come to this particular piece of code. This piece of code is doing the same thing that I had talked about. It is doing the data acquisition and feeding in this information into the USRP, thereby telling the USRP how many samples to acquire, right? From this calculate frame size, we go to the next state, which is receive data. In this receive data state, we are basically getting that data from the USRP and queuing it up. We are also plotting the constellation graph. So that non-equalized constellation, we are plotting with very raw data. That is why it was looking so skewed, right? Now, once we enqueue this element, once we enqueue this data over here, we are going to dequeue it in this loop, in the digital signal processing loop. You can see the dequeuing happening over here, right? The first thing that we do once the data goes in over here is this matched filter. You already seen the inside of this VI, so I will just show one of these to make sure that you are convinced that this is the same thing we discussed in the presentation. We find out the parameters and we convolve them with the incoming data. Okay. The first thing we do is match filter. Once the data has been filtered, this data goes to the second block, which is the symbol timing correction block. Okay. In this symbol timing correction block, we will do the same algorithm. We will find the power at different possible offsets. Whichever offset gives us the maximum possible power is the offset which we will stick to. That offset is given over here to this downsample VI. Okay. This downsample VI will take this huge chunk of data, start from the right point and take every nth sample from that data set. Now we finally have symbols. But the concern is that these symbols may be corresponding to different packets and hence may be scattered over these received waveforms. So one waveform may have symbols corresponding to 2 packets, so on and so forth. So this particular VI, firstly, what we will do, firstly, we will find out what is the correct symbol starting point. So far we had found out what is the correct sample starting point. Now we'll find out what's the correct symbol starting point. That happens through this RX detect frames. What is the logic behind this correct symbol starting point? Can someone quickly write on the chat? How were we finding the correct starting point for a frame? What were we using to find that out? Frame detection and synchronization was happening with the help of which mathematical function, which statistical function? Anyone? Cross correlation. Perfect. Thank you, Ben. So now we have cross correlation happening over here with the sync value and the incoming data stream. That cross correlation gives this max sync value. It also gives a value. It also tells about which index has that maximum sync value. Okay. Now that index is fed along with that previous waveform into this parse packets VI. This parse packets VI takes data from multiple waveforms, clubs them to give us packetized data. This packetized data has pilot symbols or training sequence in it. That pilot symbol or training sequence is then used to find out or generate the channel coefficients. The way we generate channel coefficients is by using a certain algorithm. It's called CRLB theorem, not algorithm, theorem. If someone wants details on that, you can reach out to me. So we find out those channel coefficients. Once we find out those channel coefficients, next job is to see if we can inverse those and find the coefficients for the equalizer, which will work on MSE. So we use the Penrose-Moore pseudo inverse algorithm to find the inverse of this matrix, and the resultant equalizer coefficients are fed into this last block over here. This will equalize the channel and give us the final waveform. Now here you will notice that we are plotting the equalized constellation and the equalized eye diagram, and yeah, the equalized constellation is what you were seeing on the front, and that's why you were seeing that that constellation looks so much better, because all this process has already happened on that. We demodulate this data to give us bits. We enqueue all these bits into a queue. We put these bits in a queue and we dequeue it over here in the third loop. In this third loop, the first thing that we do is that we find out the packet number. Okay, we depacketize the data. All these bit streams we depacketize to extract the data, to extract which packet number it is, to find out whether or not it's the last packet, and if there is some amount of zero padding that has happened in it. Okay, once we've done that, once we know that we have a packet, we form this packet and we add it to this array. This array keeps adding packets in every single iteration till what time? Till it reaches a size equal to this. We specify a certain size. Here we've called it 10. The moment we have around 10 packets, we move over to the next case of the state machine. In this next case of the state machine, we are basically taking in our array of packets and we are assuming that no packet drop occurred. We are sorting this packet. We are sorting all these packets and we are then in the sorted order, the sorted packets we are sending further ahead. Now, one thing that we have to realize over here is that each of these packets, once sorted, the advantage that it provides is we can simply concatenate the resulting strings together to form the original message. Once we have sorted packets, we come to the decode packets case. For anyone who's wondering that how are we transferring data between these different cases, it's by using these things called shift registers. They act as the same way that variables do in text-based programming languages. Okay. So with these shift registers, we are getting these packets out and we are decoding them, right? This is the case for Hamming decoder. This is the case for a convolutional decoder. The resulting decoded bit stream is then given to this particular sub-VI, which converts these bits to text. That text is concatenated with whatever previous text was generated, and it is updated here in the received text box. Okay, this is what you all are seeing. So this is all I had about packet transceivers, receiver algorithms. Okay. Is there anyone who has a question on either of these parts that I covered today? Please understand that this is just one way of forming packet transceiver. You can actually do a lot of, you can actually add a lot of things. Some of you might have realized that we are not talking about, things like the network layer and all at all. We are directly jumping from the application layer down to the PHY without really giving a lot of care, without, taking care of a lot of layers in between. You can always do that. So you have something called the LT application framework, which NI provides. You have something called there is also the 802.11 application framework, the Wi-Fi application framework, which NI provides. Both of these frameworks implement a lot of these protocols in complete detail. End of the day, even they are doing packet transmission, packet reception. But the algorithm which we have implemented here is our own. It's a custom algorithm. You can always keep building small modules on top of this. For example, I can add a CFO module. For example, I can add a scrambler module. I can add some other packet structure. I can add multiplexing in between, right? And I can bring it very, very close to an existing algorithm, which means that I can sit and convert this code into, let us say, a full LTE stack. It's slightly difficult, but still. And let us say you're on the other side of the spectrum, where instead of building an LTE stack from the scratch, you would rather want to do research on the LTE stack or research on the Wi-Fi stack, or you would want to do research on something else, maybe millimeter wave, right? For all those things, there are also options where you can go for stacks which are already built. NI provides these options. Of course, there are frameworks which are provided. There are also open source options. The OAI framework is there for 5G LTE, right? So, but every one of them at its core has something of this sort, an algorithm which was improved up to form a protocol level thing, right? So yeah, I mean, if no one has any other questions, if you have any questions on what I just said, what all you can try doing in terms of research, etc., please feel free to ask now. If you have no other questions, then that's all I had to cover today. I know we are ending 10 minutes early, but yeah. Anyone from IIT Jammu, sir, ma'am, are there any other things you would want to cover? Anyone on call from IIT Jammu? The attendance link was already shared. I think you'll find it in the chat window previously. So shared at around 3:30. You can scroll up messages and check. Is there any textbook somewhere we can learn more? Is there anything particular you want to learn about? Varun, is there any particular concept that you are saying, or in general?
So I'm talking about in general, like if you want to design filters like second order, third order filter, like. Okay.
Yeah, I mean, for all those concepts, you'll definitely find, a lot of textbooks. I used to refer to BP Lathi a lot when I was in college, of course. And you can also look at other textbooks. I mean, I'm not the best person to probably recommend textbooks. You're in a room which has, I think, professors as well. So they can definitely tell you more. But yeah, as for all this, I also have a small recommendation. If you are the kind of person who likes going hands-on on things, you will find a lot of open source codes written online. Okay, so pick up any any software of your choice, maybe LabVIEW, maybe GNU Radio, maybe C, Python, whatever, and try to go through some of these code libraries, maybe MATLAB, right? All these tricks, small modules, you'll learn a lot about in those. So, okay, thank you. Okay, I think it's close to 5 o'clock. If there is anyone from IIT Jammu who would like to formally conclude this, you can take over now. But that was all from my side. Thank you all for attending the session. I hope you guys learned something. Please feel free to reach out to me if there are any other questions. Thank you and have a good rest of the day. Bye-bye.